Picture a time before the cosmos as we know it existed, a time of profound and utter silence, where not a single star graced the heavens, and the universe was enveloped in an impenetrable shroud of pure darkness. This wasn't just any darkness, it was the primordial state of everything, a cold, featureless expanse that lasted for millions of years after the explosive birth of the universe. We call this mysterious chapter the Dark Ages, and it represents one of the most profound gaps in our understanding of cosmic history. It's the great unknown that sits between the brilliant flash of the Big Bang and the eventual dawn of the first stars, a period so removed from light that it remains almost entirely hidden from our most powerful telescopes, a cosmic secret locked away in time. For any of us who have ever looked up at a star-filled night sky and felt a sense of wonder, it's almost impossible to fathom a universe without any of those familiar pinpricks of light. A reality where the very ingredients for everything we see around us were still just a silent, swirling soup of fundamental particles, waiting in the shadows for their cue to assemble into the grand tapestry. Galaxies and life itself, what could possibly happen during an epoch that lasts for so long, in a universe that is essentially blind and mute? This is the question that drives astronomers and physicists to the edge of theoretical physics, piecing together clues from the faintest echoes of the past to reconstruct a history written in darkness. The very nature of this era challenges our perception of time and existence, forcing us to consider a cosmos that was fundamentally different from anything that came after. It's a detective story on the grandest possible scale, where the crime scene is the entire universe and the clues are hidden in the subtle patterns of ancient light and the very fabric of space-time. This isn't just an academic exercise, it's a journey to understand our own deepest origins, to answer the fundamental human question of where we ultimately came from, and how a universe of such breathtaking complexity and beauty could have emerged from a beginning of such simple, featureless darkness. To guide us through this shadowy epoch, we're about to explore 30 mind-bending theories that scientists have proposed to illuminate the Dark Ages. These are not just simple ideas, they are revolutionary concepts that stretch our imagination, from the possibility of dark matter driving the first collapses of structure to exotic forms of energy that may have rippled through the void. We will venture into a time where the laws of physics as we know them were being tested, and the first seeds of everything, you, me, and every star in the sky, were quietly being sown. So, join me as we pull back the curtain on this hidden era, uncovering the secrets of a universe in waiting and discovering the incredible forces that were at work in the darkness long before the first star ever blinked on. Our journey into the cosmic Dark Ages begins with a truly radical proposition, one that suggests the very first architects of structure were not stars or gas, but something far more exotic and mysterious. This is the primordial black hole seeding theory. Imagine if the universe's first building blocks weren't gentle clouds of hydrogen, but instead were incredibly dense, pinprick singularities forged in the chaotic fires of the very first moments after the Big Bang. These wouldn't be the massive black holes formed from dying stars. These would be primordial ones, potentially as small as an asteroid, yet containing the mass of an entire mountain, scattered across the darkness like invisible seeds waiting to sprout. In a universe that was otherwise almost perfectly smooth, these black holes would have been the ultimate anomalies, creating tiny, intense points of extreme gravity. Their immense gravitational pull would have started to act like cosmic magnets, relentlessly drawing in the surrounding dark matter and the sparse sea of hydrogen gas that filled the void. Over millions of years, this slow, steady accumulation would have created the very first gravitational wells, the initial pits in the fabric of space-time around which everything else would eventually coalesce. Without these seeds, the process of pulling together enough material to form a galaxy might have taken vastly longer, or perhaps unfolded in a completely different pattern. They provided a crucial head start, a ready-made foundation for structure in a cosmos that was desperate for any kind of imperfection to break the stillness. The evidence for this idea isn't just speculative. It might be written in the oldest light we can observe, the cosmic microwave background. This faint afterglow of the Big Bang carries with it a snapshot of the universe's infancy, and within its subtle temperature fluctuations, scientists have detected anomalies that are difficult to explain with standard models of cosmic evolution. Could the gravitational influence of a vast population of these tiny black holes have left its fingerprint on this ancient radiation, subtly warping it in ways we are only now beginning to decipher? It's a compelling possibility, suggesting that the Dark Ages were not entirely dark, but were instead punctuated by the silent, invisible work of these gravitational anchors, setting the stage for the spectacular dawn of light that was still to come. Now let's turn our attention to an idea that's as elegant as it is extraordinary, the cosmic string network theory. What if the universe's blueprint for structure wasn't a random scattering of seeds, but instead a vast, intricate web of cosmic filaments, threads so dense and massive that their gravity could literally pull the universe into shape? This concept proposes just that, suggesting the Dark Ages were not a time of total chaos, but a period where an invisible architecture was already in place, a framework of cosmic strings. These aren't the strings from string theory. Think of them more like incredibly thin, infinitely long cracks in the fabric of spacetime itself, relics from a phase transition in the universe's earliest, most energetic moments, similar to the cracks that form in ice as water freezes. They would have been thinner than a proton, yet a single inch of such a string could weigh more than a mountain range, possessing a gravitational pull so intense that they would have sliced through the cosmos, warping everything around them. In the profound darkness and near uniformity of the early universe, this network of strings would have been the ultimate source of structure. As they zoomed through the cosmos at near light speed, vibrating and occasionally intersecting to form loops, their immense gravity would have acted as a template. The primordial hydrogen and dark matter, which were otherwise spread almost perfectly evenly, would have felt an irresistible pull toward these ultra-dense lines of energy. Think of it like dust gathering along the strands of a spider web. The strings created the initial wrinkles in the smooth cosmic sheet. They provided the preferred locations, the rails and guide wires, along which matter could begin to flow and accumulate, creating the very first faint density fluctuations that would one day become the great cosmic web of galaxies and galaxy clusters we observe today. Without this pre-existing scaffolding, the process of going from a smooth universe to a clumpy one might have been far less efficient, or perhaps would have produced a completely different large-scale structure. The beauty of this theory lies in its potential to explain some of the largest formations we see, like the vast filamentary walls of galaxies that stretch across billions of light years. These colossal structures seem to mirror the kind of architecture a network of strings would naturally produce. While we haven't yet found direct, smoking gun evidence for cosmic strings, their potential signatures are being hunted in some of the most precise maps we have of the universe. The intense gravitational fields of these strings would act as cosmic lenses, potentially creating double images of distant objects, and their violent vibrations could have sent powerful ripples through spacetime itself, leaving a faint imprint in the cosmic microwave background or even generating gravitational waves that our most advanced observatories might one day detect. It's a theory that paints the Dark Ages not as an empty, passive wait, but as an era of dynamic, invisible construction, where the universe was quietly weaving the foundation for all the light and life to come. But to truly appreciate the next theory, we need to shift our perspective from the grand architecture of the cosmos to the behavior of its most elusive ingredient. We've talked about black holes as seeds and cosmic strings as a scaffold, but what if the key player in the Dark Ages was the dark matter itself, not just sitting idly by, but actively interacting in a way that changed the thermal history of the universe. This brings us to the fascinating and highly detailed WIMP dark matter annihilation theory. WIMP stands for Weakly Interacting Massive Particle, and it's one of the most prominent candidates for what dark matter could actually be made of. The weakly interacting part is crucial. It means these particles barely notice ordinary matter, passing through our planet, our homes, and even our bodies as if they weren't even there. But the theory proposes that during the Dark Ages they might have been noticing each other. The mechanism is as elegant as it is powerful. According to this idea, when two WIMP happen to collide, they wouldn't just bounce off one another, they would annihilate, completely converting their mass into pure energy in accordance with Einstein's famous equation, E equals mc squared. This energy would manifest as a cascade of radiation, and most importantly for the cold gas of the early universe, high-energy particles like electrons and photons. Now picture the cosmos during this era, a vast, expanding and cooling sea of hydrogen gas, growing colder and darker with every passing million years. Into this quiet, frigid scene, these annihilations would have been injecting tiny, localized pockets of heat. It wouldn't have been a cosmic firework display. It would have been more like a faint, pervasive glow of warmth, a subtle heating process happening almost everywhere at once. This gentle warming had profound consequences. For the first stars to be born, vast clouds of hydrogen needed to collapse under their own gravity, and for that to happen efficiently, the gas needed to be cold. Cold gas is sluggish and can radiate away its energy, allowing it to condense more easily. If the WIMP were constantly pumping even a small amount of energy back into this gas, they would have been working against gravity's pull. This cosmic friction could have put the brakes on star formation, effectively delaying the dawn of the first luminous objects. The Dark Ages might have been prolonged because dark matter itself was fighting against the collapse that would end them. It's a cosmic paradox where the very substance that provides most of the gravitational glue for structure could have also been subtly preventing that structure from lighting up. The hunt for evidence of this process is one of the most active areas in modern cosmology. Scientists are using our most powerful radio telescopes to search for a specific predicted signature from this era. The annihilating WIMP would have produced a very specific fingerprint on the hydrogen gas that filled the universe. They would have slightly altered the energy levels of the hydrogen atoms, affecting the characteristic radio wave signature that this gas emits, a signal known as the 21-centimeter line. By looking for a specific distortion in this ancient radio whisper, astronomers hope to find the ghostly imprint of dark matter annihilations. Detecting this signal would be a monumental discovery, not only confirming the existence of WIMP, but also revealing their active and transformative role in shaping the timeline of our cosmic history, proving that the darkness before the dawn was far from inert. While we've explored dark matter as a source of heat or a gravitational anchor, what if its true nature during the Dark Ages was far stranger and more fluid than anyone imagined? This brings us to a theory that challenges the very picture of dark matter as a collection of individual particles, proposing instead that it underwent a profound transformation, becoming a single, coherent quantum entity that literally flowed through the cosmos. This is the action dark matter condensation theory, and it hinges on the properties of a hypothetical particle known as the axion. Conceived to solve a deep puzzle in particle physics concerning the symmetry of nuclear forces, axions are theorized to be incredibly light, potentially trillions of times lighter than an electron, and exceedingly weakly interacting. Because of their unique quantum properties, trillions upon trillions of these particles could be passing through you every second without a trace. The magic begins when we consider what happens to a vast number of these ultra-light particles as the universe expanded and cooled during the Dark Ages. Under the right conditions of extreme cold and density, a remarkable quantum phenomenon can occur, something known as a Bose-Einstein condensate. In this exotic state of matter, individual particles lose their identities and merge into a single, unified quantum wave, behaving less like a swarm of discrete objects and more like a single, coherent fluid. Think of it like this. Imagine a crowded room where everyone is talking and moving independently. That's normal matter. Now, imagine if suddenly the entire crowd began to move in perfect, synchronized harmony, acting as one single fluid entity. That is the essence of a condensate. According to this theory, the actions that make up dark matter did exactly this, condensing into a cosmic-wide superfluid that permeated the entire universe. This shift from a collection of cold, collisionless particles to a unified superfluid would have dramatically altered how dark matter shaped the cosmos. A superfluid has unique properties. It can flow without any friction or viscosity, and it can develop intricate, swirling patterns known as vortices. In the context of the Dark Ages, this superfluid dark matter would have been capable of smoothing out certain gravitational inconsistencies that the standard model of cold dark matter struggles to explain. For instance, our simulations of galaxy formation often predict that small, dwarf galaxies should have incredibly dense centers, but observations show their dark matter is more evenly distributed. This is known as the cusp core problem. A dark matter superfluid offers an elegant solution. Because it is a fluid, it can be stirred and mixed, its inherent quantum pressure preventing it from collapsing into those overly dense, sharp cusps at the centers of small galaxies, instead naturally forming the softer cores we actually observe. Furthermore, the behavior of this action condensate could have directly influenced the formation of the very first structures. Instead of just sitting passively in gravitational wells, this superfluid would have sloshed and rippled, creating intricate wave-like patterns on a quantum scale. These quantum waves could have imprinted specific signatures on the distribution of both dark and ordinary matter, potentially seeding a different pattern of tiny galaxies and star clusters than other models predict. The presence of this cosmic superfluid would mean the Dark Ages were not just a time of silent gravitational collapse, but also a period of subtle quantum mechanical choreography, where the fundamental fabric of the dark universe was flowing and organizing itself according to rules we are only beginning to grasp. The hunt for evidence of this theory is twofold. Particle colliders like the Large Hadron Collider are searching for the action particle itself, while astrophysicists are using ultra-precise maps of the cosmic microwave background and the large-scale structure of the universe to look for the unique, smoothed-out gravitational footprints that only a dark matter superfluid could have left behind. Just as we ponder dark matter's role in sculpting the cosmos, we must also consider the force that governs its expansion on the largest scales. This brings us to a truly mind-bending proposal that rewinds the clock on one of modern cosmology's biggest discoveries. We are all familiar with dark energy, that mysterious force causing the universe's expansion to accelerate today. But what if that wasn't its first appearance on the cosmic stage? The early dark energy decay theory dares to suggest that a different, transient form of dark energy briefly dominated the universe long before the stars ignited, during the heart of the Dark Ages themselves. This wasn't the constant force we observe now. It was a fleeting entity, a burst of repulsive energy that surged and then faded away, leaving a subtle but crucial mark on the timeline of creation. To understand its potential impact, let's visualize the universe during this era. After the initial fireball of the Big Bang, the cosmos was expanding, but the relentless pull of gravity from all the matter and dark matter was steadily slowing that expansion down. It was a cosmic tug-of-war, and gravity was winning. Now, introduce this early dark energy. Think of it as a sudden, powerful counterforce, an anti-gravity push that surged into prominence for a short cosmic moment. For a period that might have lasted only a few million years, this energy would have made the universe expand faster than it otherwise would have. It was a brief cosmic inflation of sorts, but happening billions of years after the initial one that shaped the universe's very first moments. This temporary speeding up would have had a profound effect on the embryonic structures trying to form in the darkness. Imagine those first wisps of slightly denser gas and dark matter, slowly beginning to collapse under their own gravity to form the seeds of the first galaxies. As they begin their inward fall, the fabric of space itself starts stretching faster because of this early dark energy. This rapid stretching acts like a cosmic tension pulling against the gravitational collapse. It becomes much harder for those delicate overdensities to hold themselves together and condense. The consequence, the formation of the very first largest-scale structures could have been significantly delayed. The universe would have had to wait for this early dark energy to decay away, to vanish back into the quantum vacuum from which it came before gravity could properly resume its work. This means the dark ages might have been extended, and when structures finally did form, their initial sizes and distribution could carry a unique signature of this early accelerated phase. The implications ripple forward to one of the most important events in cosmic history, the epoch of reionization, when the light from the first stars and galaxies ripped electrons from neutral hydrogen atoms and lit up the cosmos. If the formation of those first structures was delayed by this early dark energy, then the entire schedule of reionization would have been pushed back. The cosmic dawn would have arrived later on the universal clock. This creates a testable prediction. Our most powerful telescopes, like the James Webb Space Telescope, are peering back to observe the very first galaxies and quasars. The timing of their emergence and the specific pattern of how they reionize the universe could either support or challenge this theory. If we find that reionization started surprisingly late given other cosmic parameters, it could be a compelling piece of evidence that an early form of dark energy once put the brakes on star formation. Furthermore, the theory offers a potential solution to a lingering tension in modern cosmology, the Hubble tension. This is the puzzling discrepancy between the measured rate of the universe's current expansion using local indicators and the rate predicted from the afterglow of the Big Bang. An early, fleeting episode of dark energy acceleration could have subtly altered the expansion history in a way that resolves this disagreement, making the observations from the early and modern universe align more perfectly. It's a theory that not only illuminates the shadows of the Dark Ages, but also seeks to heal a rift in our understanding of the cosmos across its entire lifespan, suggesting that the dark energy we see today might just be the final act of a phenomenon that has manifested in more than one guise throughout the deep history of everything. As we venture deeper into the cosmos's most enigmatic era, we now confront a concept so exotic it seems to belong to the realm of pure speculation, yet it holds a compelling place in theoretical physics. This is the magnetic monopole catalysis theory. To grasp its potential role in the Dark Ages, we first need to understand what a magnetic monopole actually is. In our everyday experience, every magnet, from a simple refrigerator magnet to the Earth itself, always has two poles, a north and a south. If you break a magnet in half, you don't get isolated north and south poles. You simply get two new magnets, each with its own pair of poles. This duality is a fundamental feature of the electromagnetism we know, but some of the most ambitious theories of particle physics, particularly grand unified theories which attempt to merge the electromagnetic, weak and strong nuclear forces, predict that in the extreme energies of the very early universe, particles carrying just a single magnetic pole should have been created. These are the magnetic monopoles, hypothetical particles that are essentially isolated north or south magnetic charges, behaving like fundamental, point-like magnets. The existence of even a sparse population of these relics coursing through the dark, primordial universe would have had consequences far beyond their rarity. The most dramatic of these is a process known as the Rubikov-Kalin effect. This theoretical mechanism suggests that if a magnetic monopole were to encounter something as common as a proton, one of the fundamental building blocks of all atomic nuclei, it could act as a catalyst triggering the proton's decay. Now, protons are considered incredibly stable. Under standard conditions, they are thought to live for an unimaginably long time, perhaps longer than the current age of the universe. But in the presence of a monopole, this stability could be shattered. The monopole wouldn't be consumed in the reaction. It would simply facilitate it like a key unlocking a door, allowing the proton to fall apart into lighter particles such as a positron and mesons, releasing a burst of energy in the process. Now paint this picture onto the canvas of the Dark Ages. The universe is a vast, cold, and dark expanse, filled with a diffuse, neutral sea of hydrogen gas. The dominant activity is the slow, silent pull of gravity, gently coaxing this gas into the first faint structures. But drifting through this stillness are these rare, powerful catalysts, the magnetic monopoles. Every time one of them collided with a proton in the hydrogen gas, it would have initiated a miniature explosion. A tiny, localized point of energy would flare into existence, injecting high-energy particles and radiation into the surrounding primordial environment. While each event would be insignificant on its own, over millions of years and across the vast volume of the cosmos, this process could have created a faint, pervasive background of radioactivity and heat. It would have been a subtle, sputtering source of energy in an otherwise frigid and passive cosmos. This persistent, low-level energy injection could have subtly influenced the nascent chemistry of the early universe. The high-energy particles released from proton decay would have ionized the nearby hydrogen gas, knocking electrons free from their atoms and creating small, temporary pockets of plasma. This would have slightly altered the ability of the gas to cool and collapse, potentially affecting the delicate balance required for the first star-forming clouds to condense. Furthermore, the decay products themselves would have introduced new elements into the mix. The primordial universe after Big Bang nucleosynthesis was almost entirely hydrogen and helium. There were no heavier elements. But the debris from these catalyzed proton decays would have included trace amounts of other particles, potentially seeding the environment with the first, ultra-rare ingredients for a more complex chemistry long before the first stars began their nuclear fusion. The Dark Ages, in this view, were not completely sterile. They were punctuated by these rare, energetic events, a faint radioactive whisper hinting at processes that transcended the ordinary laws of physics. The legacy of these monopoles, if they ever existed, might be imprinted on the universe we see today. One potential signature is the abundance of light elements. The specific energy and particles released by monopole-catalyzed proton decay could have left a subtle, altered fingerprint on the primordial ratios of elements like lithium and helium. While current observations match the predictions of standard Big Bang nucleosynthesis quite well, even tiny deviations could one day be traced back to such exotic processes. Another tantalizing possibility is that a very small number of these primordial monopoles could still be drifting through the universe today. Experiments deep underground, shielded from cosmic rays, have been searching for these elusive particles for decades. Finding just one would be a revolutionary discovery, not only confirming a key prediction of grand unified theories, but also providing a direct relic from the Dark Ages, a silent witness to a time when the universe was dark, simple, and possibly crackling with the faint, transformative energy of decaying protons. Building on the theme of transformation, we arrive at a concept that strikes at the very bedrock of reality itself. We operate under the assumption that the laws of physics are universal and unchanging, that the rules governing atoms here and now are identical to those in the most distant galaxy and the farthest past. But what if that foundational premise is wrong? The varying fundamental constants theory dares to propose exactly that, suggesting that during the profound isolation of the Dark Ages, the very constants of nature might have been subtly shifting. Among the most critical of these is the fine structure constant, a dimensionless number that governs the strength of the electromagnetic force. It is this force that dictates how tightly electrons bind to atomic nuclei, how atoms interact with light, and essentially how all of chemistry works. A change in this constant, even by a minuscule fraction of a percent, would have sent ripples of change through the entire cosmic narrative. To grasp the sheer power of this idea, consider the delicate balance within a single atom of hydrogen, the sole ingredient of the primordial universe. The energy levels of its electron, the specific wavelengths of light it can absorb and emit, are all exquisitely tuned by the value of the fine structure constant. Now picture the vast, dark clouds of this hydrogen gas, slowly cooling and preparing for the gravitational collapse that will birth the first stars. Their ability to cool down is absolutely paramount. A cloud cools by radiating away its thermal energy, and in the early universe, this happened primarily through the hydrogen atoms colliding, exciting their electrons, and then releasing that energy as faint radiation, particularly in a specific spectral line. The efficiency of this entire process, how quickly the cloud can shed its heat and condense, is directly wired into the value of that fundamental constant. If the fine structure constant were slightly larger during the Dark Ages, the electromagnetic force would have been stronger. This would have made atomic bonds tighter, altering the energy levels in the hydrogen atom and potentially making it much more efficient at radiating away heat. A gas cloud in this scenario could cool with breathtaking speed, collapsing into dense, fragmenting clumps that might form scores of low-mass stars. Conversely, if the constant were slightly smaller, the electromagnetic force would have been weaker. Atomic transitions would have been less efficient, and the primordial gas would have been far more sluggish at losing its heat. In this altered reality, the gas would struggle to cool, resisting collapse. When it finally did succumb to gravity, it would likely form far fewer but much more massive and monolithic stars. The timeline and the very character of the first stellar generation would have been completely different. A universe with varying constants might have seen the first stars flicker on millions of years earlier or later than in our standard models. It could have produced a first wave of stars that were predominantly small, red, and long-lived, or instead, a population of brilliant blue titans that lived fast, died young, and polluted the cosmos with heavy elements at a dramatically different rate. The consequences would cascade forward, influencing the types of planets that could eventually form and perhaps even the potential for life itself. The evidence for such a radical idea is, as one would expect, incredibly subtle but is the subject of intense scientific scrutiny. Astronomers hunt for these variations by using the universe itself as a giant laboratory. They point our most powerful telescopes at incredibly distant quasars whose light has traveled for billions of years to reach us. As this light passes through ancient clouds of interstellar gas, specific atoms imprint a fingerprint of absorption lines on the spectrum. The precise spacing and positions of these lines are exquisitely sensitive to the value of the fine structure constant. By comparing these ancient fingerprints to the ones we measure in laboratories on Earth today, scientists can probe whether the constants have remained truly constant. Some tantalizing and still controversial analyses have suggested there might be a very slight variation in certain directions of the sky, a suggestion that, if confirmed, would force a complete rewrite of our physics textbooks. This theory pushes our understanding to the limit, forcing us to contemplate a universe whose fundamental rules are not written in stone, but are more like preferences that can evolve over time. It transforms the Dark Ages from a mere passive backdrop into a potential era of fundamental transition, where the laws of physics themselves might have been settling into their current form. The quiet, dark cosmos becomes a stage for a drama not just of matter and energy, but of the very parameters that define reality, suggesting that the stage itself was still under construction. To truly grasp the significance of this next concept, we need to revisit the very first moments of time. The prevailing cosmological model tells us that the universe's initial conditions were set by a period of rapid inflation, and the tiny quantum fluctuations it generated were what we call Gaussian. In simple terms, this means the distribution of these early density variations, the slight over-densities and under-densities that would one day become galaxies and voids, was essentially random and followed a very specific bell curve-like pattern. You could think of it like the static on an old television screen, a mostly even, random crackle of hot and cold spots. This Gaussian assumption is the bedrock upon which most of our simulations of cosmic evolution are built, predicting a relatively orderly, statistical progression from smoothness to structure. But what if that foundational noise wasn't so random after all? What if the cosmic dice were subtly loaded? This is the radical proposition of primordial non-Gaussianity. This theory posits that the initial fluctuations from inflation deviated from this perfect Gaussian randomness. Instead of a gentle, static-like distribution, there were unexpected correlations and connections between these fluctuations. Some regions of space were not just slightly denser by chance. They were part of a coordinated, statistical anomaly that made them exponentially more dense than the Gaussian model would ever allow. Imagine the static on that television screen suddenly organizing itself, with clusters of bright white pixels grouping together to form intensely hot spots far brighter than any individual pixel could be on its own. In the cosmic context, this would have created rare but extraordinarily potent seeds of density scattered throughout the infant universe. Now, let's project this idea forward into the Dark Ages. In a standard Gaussian universe, the process of structure formation is a slow, grinding affair. Gravity acts on the slight over densities, pulling in more and more matter over hundreds of millions of years, eventually forming the first stars and small protogalaxies. But in a non-Gaussian universe, the game changes completely. Those rare, ultra-dense regions predicted by this theory wouldn't need to wait. Their immense density would give them a colossal gravitational head start. While the rest of the cosmos was still a quiet, slowly stirring soup, these specific locations would have experienced a runaway gravitational collapse almost immediately. The gas and dark matter in these areas wouldn't just slowly coalesce, they would plummet inward at a ferocious rate. The consequence of such a rapid, powerful collapse is staggering. It could lead to the formation of objects so massive they defy our conventional understanding of early star formation. Instead of the first stars being a few hundred times the mass of our Sun, these non-Gaussian seeds could have directly forged supermassive stars, behemoths containing tens of thousands or even hundreds of thousands of solar masses. These would not be ordinary stars. They would burn through their nuclear fuel at a prodigious rate, living for only a few million years before their cores collapsed under their own immense weight. And that collapse wouldn't just form a typical stellar black hole. It would create a massive black hole seed right from the outset, a heavyweight champion born directly from the darkness. This provides a direct and elegant solution to one of the most persistent puzzles in modern astronomy: the existence of supermassive black holes powering brilliant quasars when the universe was less than 1 billion years old. In a standard Gaussian model, it's incredibly difficult to grow a black hole from a small stellar remnant to a billion solar mass giant in such a short cosmic time. But if the seeds were already hundreds of thousands of solar masses from the very beginning, their path to quasar status becomes a much more plausible, direct line of growth. The hunt for evidence of this non-Gaussian signature is a major focus of observational cosmology. Scientists are meticulously analyzing the most detailed maps we have of the early universe, the cosmic microwave background from missions like Planck, and the large-scale structure of galaxies from surveys like the Sloan Digital Sky Survey. They are searching for statistical anomalies in the distribution of hot and cold spots and in the clustering of galaxies that would betray those initial correlations. Finding a definitive signal of non-Gaussianity would be more than just a minor adjustment to our models. It would be a revolution, forcing us to rewrite the story of inflation and the very first moments of creation. It would reveal an early universe that was not a place of gentle, random noise, but one punctuated by dramatic, predetermined peaks, where the fate of the first supermassive black holes was sealed in the first trillionth of a second of time, setting the stage for the brilliant but fleeting dawn of the first quasars. Now let's introduce a character that is both ghostly and potentially transformative. We've discussed dark matter as WIMP and as a superfluid, but what if it was something even more ethereal, a particle that is almost a perfect shadow of one we already know? This is the compelling premise of the sterile neutrino dark matter theory. To understand it, we first need to talk about its well-known relatives, the standard neutrinos. Trillions of these nearly massless, chargeless particles are streaming through you every second, emanating from the Sun, from distant supernova, and from the Big Bang itself. They are famously aloof, interacting with ordinary matter only through the weak nuclear force and gravity, making them incredibly difficult to detect. The sterile neutrino is a hypothetical heavyweight cousin to these phantoms. It's sterile because it wouldn't even interact via the weak force. Its only connection to the rest of the universe would be through the gentle tug of gravity and through its ability to oscillate or transform into the regular neutrinos we know. If these sterile neutrinos are real and have a specific mass, thought to be in the range of a few kilo-electronvolts, making them millions of times heavier than their standard counterparts, but still incredibly light by particle standards, they become a prime candidate for what dark matter could be. And here is where the theory gets truly fascinating for the Dark Ages. Some models suggest these particles are not entirely stable. They could spontaneously decay. The process would be exceedingly slow. A single sterile neutrino might live for ages, but across the vast population that would constitute the dark matter of the entire cosmos, these decays would be happening constantly. And when one decays, it wouldn't just vanish, it would transform typically into an ordinary light neutrino and a burst of radiation, most often in the form of an X-ray photon. Now envision the universe during its long, dark silence. It is filled with this immense, invisible ocean of sterile neutrino dark matter. And all throughout this ocean, there is a continuous, faint shimmering happening, a universe-wide, incredibly soft glow of X-ray radiation emanating from the dark matter itself. This isn't a brilliant light, it's more like the deepest, most pervasive background hum of energy, a whisper of high-energy photons being born from the decay of the invisible. This constant, low-level radiation bath would have had a profound effect on the one thing that was present, the primordial hydrogen gas. As these X-ray photons traveled through the neutral hydrogen, they would have been proficient at knocking electrons loose from their atoms, a process known as ionization. But unlike the intense ultraviolet light from the first stars that would later rip the universe apart, this was a gentle, persistent ionization happening everywhere at once. This process slowly but surely heated the gas. Think of it as a cosmic space heater, set on the very lowest setting but left on for millions of years. The vast intergalactic medium, which should have been growing colder and colder as the universe expanded, was instead being kept subtly warm by this energy input from decaying dark matter. This warm, intergalactic medium had a critical impact on the smallest structures trying to form. For a small cloud of gas to collapse and form a small, dwarf galaxy, its gravity needs to overcome both the expansion of the universe and the internal pressure of the gas. Cold, dense gas has low pressure and collapses easily. Warm, ionized gas has higher pressure and fights back against gravitational collapse. The persistent warming from sterile neutrino decays would have made it exceptionally difficult for these small, faint galaxies to ever get started. Their shallow gravitational potential simply couldn't compete with the added thermal pressure. The result would be a suppression of the formation of the smallest, earliest galaxies. This provides a potential solution to a puzzling mismatch between our cosmic simulations and our observations, known as the missing satellites problem. Our best models of galaxy formation predict that thousands of small dwarf galaxies should be orbiting large galaxies like our own Milky Way, yet we only observe a few dozen. If sterile neutrino dark matter was gently heating the universe during the Dark Ages, it could have prevented the vast majority of these small galactic building blocks from ever forming, naturally explaining why we see so few of them today. The legacy of this theory is therefore written in the galactic fossil record. Astronomers are actively searching for the two key signatures of this idea. The first is the specific X-ray emission line that will be produced by the decay of a sterile neutrino with a given mass. They scour the X-ray spectra of distant galaxy clusters and even the diffuse background of the universe, looking for a faint spike at a specific energy that has no other explanation. The second is the detailed census of ultra-faint dwarf galaxies around the Milky Way. If their numbers and properties align with the predictions of a warm, dark matter model, it would be a powerful indirect confirmation that the darkest era of the universe was in fact faintly illuminated by the slow death of its own most mysterious component. So far, we've considered dark matter as an anchor for gravity, a source of heat, and even a cosmic superfluid, but always acting at a distance, its influence felt but its substance untouched. But what if that fundamental aloofness wasn't always the case? This brings us to a theory that imagines a time when the two dominant components of the universe, the ordinary and the dark, were on speaking terms. This is the baryon dark matter scattering theory. In our standard model, dark matter particles pass through the ordinary atoms that make up stars, planets, and us, as if they were ghosts walking through a wall. The two substances coexist in the same space but are utterly oblivious to one another, their only connection being the mutual pull of gravity. This theory dares to suggest that in the dense, hot early universe that wasn't entirely true. It proposes that dark matter particles and baryons, the protons and neutrons that constitute normal matter, could have engaged in a very faint but consequential interaction through a force other than gravity. Think of it not as a collision in the way two billiard balls smack into each other, but as a subtle, persistent nudge. A dark matter particle whizzing through a cloud of primordial hydrogen gas wouldn't just fly straight through untouched. Instead, it would experience a tiny, feeble scatter off a proton or an electron, a gentle exchange of momentum and energy. In today's vast, diffuse universe, such an event would be so incredibly rare as to be negligible. But during the Dark Ages, conditions were different. The universe was much smaller and denser, and this feeble interaction, repeated quadrillions of times across millions of years, could have added up to a transformative effect. It would have acted as a form of cosmic friction, a drag force between the dark and light components of the cosmos. The most critical consequence of this scattering was a transfer of heat. In the earliest phases of the Dark Ages, the dark matter was likely the colder of the two components. It had effectively stopped interacting with anything and was simply cooling as the universe expanded. The ordinary matter, the hydrogen gas, was also cooling, but it had a more recent history of interaction with the fading afterglow of the Big Bang. This scattering process would have provided a channel for the slightly warmer baryonic gas to transfer its thermal energy to the colder dark matter. Essentially, the normal matter was heating up the dark matter. While this might sound like a minor detail, it had a dramatic impact on the fate of the very first structures trying to form. For a cloud of gas to collapse and form stars, it must be able to cool down. A hot, pressurized gas resists collapse. It's like trying to compress a spring. The scattering was effectively preventing the gas from cooling efficiently, especially within the smallest gravitational wells, the halos of dark matter that were the cradles for the first proto-galaxies. These small halos have very shallow gravitational potentials. They simply don't have the pulling power to overcome internally hot, pressurized gas. So, while gas would fall into these small halos, this persistent scattering would keep it just warm enough that it couldn't condense and fragment into the first stars. This provides a beautifully elegant solution to one of the most persistent puzzles in modern cosmology, the too big to fail and missing satellites problems. Our most sophisticated supercomputer simulations of galaxy formation, which assume the standard, non-interacting dark matter, predict that our Milky Way galaxy should be surrounded by hundreds, if not thousands, of small, dark, satellite dwarf galaxies. Yet when we look at the sky, we only find a few dozen. It's as if the vast majority of these small building blocks failed to ever light up. The baryon dark matter scattering theory explains this failure perfectly. Those smallest dark matter halos did form, just as the simulations predict, but the gas within them was kept too warm by this scattering process to ever collapse and form stars. They remain to this day as entirely dark galaxies, invisible halos of dark matter that failed to ignite, their stellar potential extinguished by a faint whisper of an interaction that occurred billions of years ago. The evidence for this is written in the galactic fossil record. Astronomers are now using the observed properties of the faintest dwarf galaxies we can see to put stringent limits on the possible strength of this interaction. If the scattering was too strong, no small galaxies would have formed at all. The fact that we see some, but not the overwhelming number predicted, points to a very specific, very feeble interaction strength, a ghost of a force whose primary legacy was to leave the earliest cosmos a little bit darker for a little bit longer. Now we turn our attention from the subtle whispers of dark matter interactions to a discovery that is anything but subtle, a set of colossal, enigmatic structures that have been glimpsed at the very edge of observable time. This is the cosmic dawn blob theory. Using some of our most powerful telescopes tuned to specific frequencies of light, astronomers have managed to map the distant universe at a time corresponding to the end of the Dark Ages and the very beginning of the cosmic dawn. And what they found was startling: immense, faintly glowing clouds of hydrogen gas sprawling across tens of thousands of light years. These aren't galaxies as we know them. They are vast, amorphous structures, so enormous and diffuse that they earned the simple yet evocative name blobs. Their sheer size and luminosity present a puzzle. What cosmic engine could possibly power such gigantic beacons, illuminating these incredible volumes of primordial gas? The leading hypothesis is as dramatic as the blobs themselves. These colossal structures may be the burial mounds of the universe's very first generation of stellar titans. We're not talking about the first ordinary stars here, but a hypothetical class of objects known as population 3 stars. These would have been behemoths composed purely of the pristine hydrogen and helium forged in the Big Bang, completely devoid of the heavier elements that help later stars regulate their formation and death. Freed from these constraints, they could have grown to almost unimaginable scale stars with masses hundreds of times that of our Sun, and in the most extreme scenarios, true monsters reaching up to 1,000 solar masses or more. A single one of these stars would have burned with a ferocious intensity, pumping out ultraviolet radiation at a rate millions of times greater than our Sun. Alternatively, some models suggest that the gravitational conditions within these dense blobs were so extreme that they bypassed star formation entirely. Instead of fragmenting into many stars, a giant cloud of gas could have collapsed directly inward in a single catastrophic event to form a massive black hole seed containing tens of thousands of solar masses right from the outset, a direct collapse black hole. Whether it was a supermassive star or a direct collapse black hole, the effect on the surrounding darkness would have been revolutionary. For millions of years, the universe had been a neutral fog where hydrogen atoms kept their electrons bound. But the intense ultraviolet radiation pouring from one of these primeval powerhouses would have acted like a cosmic blowtorch. It would have ripped the electrons away from the hydrogen atoms in a process known as ionization, creating a growing, spherical bubble of transparent, ionized plasma within the opaque neutral hydrogen. This is the key connection. These vast blobs of glowing hydrogen we observe are likely the signatures of these very first ionized bubbles. The gas within them is glowing because it's being energetically illuminated and heated by a central, immensely powerful source that we often cannot see directly, either because the star has already died in a spectacular supernova or because the central engine is a black hole itself. The life cycle of these objects was incredibly brief, but their impact was permanent. A supermassive star, for all its power, would have lived for only a few million years before its core collapsed, likely producing a hypernova explosion of unbelievable energy or directly forming a massive black hole. A direct collapse black hole, once formed, would have begun voraciously accreting the surrounding gas, becoming a brilliant early quasar. In both cases, their death throes would have seeded the surrounding blobs with the first heavy elements, polluting the pristine cosmic environment and forever changing the chemistry for the next generation of stars. More importantly, the ionized bubbles they created were the beachheads of light in the war against darkness. They were the first regions where light could travel freely, the first safe zones for subsequent starlight to propagate. As more of these objects ignited across the cosmos, their individual bubbles grew and eventually overlapped, a process that culminated in the epoch of reionization, when the entire universe was permanently transformed from a neutral fog to the transparent cosmos we inhabit today. These mysterious blobs are therefore not just cosmic curiosities, they are the fossilized footprints of the universe's very first revolutionary acts, the places where darkness was first pushed back on a grand scale, heralding the dawn of a new, luminous age. Now we journey into one of the most elegant and ambitious extensions of our current understanding of physics, a concept that suggests the Dark Ages were punctuated by the final, fading echoes of a more symmetric cosmos. This is the supersymmetric particle decay theory. To grasp its significance, we need to understand the grand idea of supersymmetry itself. It's a proposed fundamental symmetry of nature that posits a profound and beautiful link between the two great families of particles, the fermions, which are the building blocks of matter like quarks and electrons, and the bosons, which are the force carriers like photons and gluons. For every known fermion, supersymmetry predicts a heavier, supersymmetric shadow boson partner, and for every known boson, a heavier fermion partner. This theoretical framework isn't just for mathematical elegance, it solves deep puzzles in particle physics and provides a perfect, natural candidate for dark matter, the lightest supersymmetric particle, or LSP. In a perfectly supersymmetric universe, these partner particles would all be stable and abundant. But we don't live in that universe. We live in one where supersymmetry is broken, meaning these superpartners are incredibly massive and have long since decayed away. The theory proposes a fascinating twist, however, that the LSP, while stable on its own today, was not always completely inert. In the earliest moments, a slightly heavier, next to lightest supersymmetric particle, or NLSP, could have been abundant. This NLSP would have been unstable, eventually decaying into the stable LSP that we now suspect forms the cosmic dark matter. But crucially, this decay process didn't necessarily all happen instantly in the first second after the Big Bang. A fraction of these NLSP could have had remarkably long lifetimes, persisting for millions of years and decaying throughout the heart of the Dark Ages itself. Imagine the scene, a universe enveloped in darkness, its primordial gas cooling in the void. Suddenly and silently all across the cosmos, these relic NLSP begin their final transformation. Each decay would have been a miniature firework of fundamental physics, converting the mass of the heavy superpartner into a burst of energy and a shower of standard model particles. This wouldn't be a brilliant flash of light, but a pervasive, universal drizzle of high-energy radiation and exotic particles. The energy released in each event would have subtly heated the intergalactic medium, providing a gentle but persistent source of warmth that could have influenced the cooling rates of the first gas clouds, potentially delaying star formation. But the truly transformative aspect might have been in the particles themselves. The decay products could have included not just photons and electrons, but also more exotic entities like positrons, or even the theoretical particles known as axions or gravitinos. This has a staggering implication for cosmic chemistry. The universe after Big Bang nucleosynthesis was a remarkably simple place, composed of about 75% hydrogen and 25% helium by mass, with only trace amounts of lithium. There were no heavier elements, no carbon, no oxygen, nothing required for planets or life as we know it. The energetic particles from supersymmetric decays, however, could have initiated a form of exotic nucleosynthesis. High-energy protons and neutrons spalled off from these decays could have collided with the nuclei of the primordial hydrogen and helium, potentially fusing them into minute, trace quantities of heavier elements like lithium, beryllium, and boron. This would have been a form of cosmic enrichment happening hundreds of millions of years before the first stars ever ignited, a faint pre-pollution of the cosmos with the seeds of complexity, all originating from the death throes of particles from a higher symmetry. Furthermore, the collective radiation from these countless decays would have created a unique background glow across the universe, a fossil radiation field distinct from the cosmic microwave background. This supersymmetric background would have been richest in X-rays and gamma rays, bathing the entire cosmos in a deep, penetrating light. This universal illumination would have contributed to the ionization of the neutral hydrogen fog, helping to keep the universe slightly more transparent even before the first stars switched on. The hunt for the evidence of this theory is a multi-pronged effort. Particle physicists at the Large Hadron Collider are desperately searching for any direct sign of a supersymmetric particle, which would instantly validate the entire framework. Meanwhile, astrophysicists scrutinize the precise abundances of the light elements in the oldest stars, looking for subtle discrepancies that cannot be explained by standard Big Bang nucleosynthesis alone, anomalies that could point to this early, exotic enrichment process. It's a theory that connects the most esoteric realms of theoretical physics with the practical history of our cosmos, suggesting that the long, dark silence was actually filled with the quiet, transformative decay of particles from a more perfect, symmetric state of existence. But what if those very first stars weren't powered by nuclear fusion at all? What if their light came from a source that was, quite literally, dark? This brings us to a truly mind-bending concept, the first stars as dark matter annihilators theory. We typically imagine the first stars as colossal, searingly hot balls of pure hydrogen and helium, fusing these elements in their cores to generate immense heat and light. But this theory paints a radically different picture. It proposes that some of these first stars may have formed around an incredibly dense, concentrated core of dark matter particles, and that it was the annihilation of this dark matter, not nuclear fusion, that provided their power. These hypothetical objects have been given a name that perfectly captures their paradoxical nature: dark stars. Imagine a stellar object unlike any we see today. Instead of a compact, blazing sphere, a dark star would have been a puffy, diffuse giant, potentially stretching across the entire breadth of our solar system. Its surface would have been relatively cool, perhaps only a few thousand degrees, glowing with a soft red or orange light, rather than the fierce blue-white of a massive fusion-powered star. This is because the energy source was fundamentally different. At the heart of this behemoth, a dense knot of dark matter particles, likely WIMP, would have been constantly colliding and annihilating each other, converting their mass directly into energy as per Einstein's famous equation. This energy would then heat the enormous envelope of ordinary hydrogen and helium gas from the inside, causing it to glow and expand to a truly gargantuan size. It would be a star lit from within by the fire of invisible matter. This dark matter power source had a profound consequence: longevity. A massive fusion-powered population 3-star is a cosmic mayfly. It burns through its nuclear fuel with such ferocious intensity that it can exhaust itself in just a few million years, ending its life in a spectacular supernova. But a dark star, powered by the gradual annihilation of its dark matter core, could theoretically shine for millions or even hundreds of millions of years. It wouldn't be racing toward a violent end. It would be in a state of sustained, stable equilibrium, glowing softly for an epoch. This completely upends our traditional timeline for the early universe. If a significant number of the first luminous objects were these long-lived dark stars, the era of the first light would have been characterized by a persistent, gentle glow from these giants, rather than the brief, brilliant flashes of the first fusion stars. The cosmic dawn would have been a slow, prolonged sunrise, not a sudden flash of lightning. The formation of such an object relies on a delicate cosmic dance. As a primordial cloud of gas and dark matter begins to collapse under gravity, the dark matter particles, which normally just buzz around in a vast halo, can become gravitationally trapped and concentrated at the very center of the forming protostar. If the density of dark matter in that central region becomes high enough, the rate of particle collisions and annihilations skyrockets. The energy released by this process can become so immense that it halts the gravitational collapse of the gas long before the core ever becomes hot and dense enough to ignite nuclear fusion. The star stabilizes in this inflated state, a balancing act between gravity's inward pull and the outward pressure from dark matter heating. It's a completely different path of stellar evolution, one where the star's fate is tied to the abundance of dark matter in its environment rather than just the mass of its gas. The eventual fate of a dark star is as fascinating as its life. Once it finally exhausts the dark matter fuel in its immediate vicinity, either by annihilating it all or through dynamical processes that scatter the dark matter core, the support mechanism vanishes. The puffy giant would then begin a final, catastrophic gravitational collapse. This collapse could trigger the onset of conventional hydrogen fusion under incredibly dense conditions, potentially leading to the formation of a supermassive star that would live a very short, violent life. Alternatively, the entire structure could collapse directly into a massive black hole, providing a direct and efficient pathway to create the heavy black hole seeds needed to explain the supermassive black holes we see in the early universe. So, these dark stars could have been the quiet, long-lived precursors to the most violent and energetic objects in the cosmos, a gentle giant phase that ultimately gave birth to cosmic monsters. While we have not yet definitively observed a dark star, their unique properties give astronomers a specific signature to hunt for. Their immense size and relatively cool surface temperature would make them appear as very faint, deeply reddened points of light at extreme distances. The James Webb Space Telescope, with its unprecedented sensitivity to infrared light, is perfectly suited to search for such objects at the edge of time. Finding even one would be a revolutionary discovery, forcing us to rewrite the chapter on the first stars and acknowledge that the universe's initial light may have been kindled not by the fires of nuclear fusion, but by the silent, ghostly annihilation of its own dark essence. Could the universe before the Big Bang have left fingerprints on the era that followed? This is the profound question at the heart of the pre-inflationary remnant theory, a concept that stretches our understanding of cosmic origins to the absolute limit. We often think of the Big Bang as the ultimate beginning, but many cosmologists now believe it was followed by an unimaginably brief period of hyper-expansion called inflation, which smoothed and stretched the infant cosmos. Yet this theory dares to ask, what if inflation wasn't completely perfect? What if it didn't erase everything that came before? The tantalizing possibility is that some incredibly robust structures, forged in a pre-inflationary epoch we can scarcely comprehend, might have survived this cosmic ironing process. These wouldn't be particles or energy, but something far more exotic, topological defects which are essentially kinks or cracks in the very fabric of space-time, stable relics from a phase transition in the fundamental fields of reality. Think of it like this: when water freezes into ice, the process isn't always perfectly uniform. Defects like cracks and bubbles can get trapped in the ice as it solidifies. In a similar way as the hyper-dense, hot universe underwent its own rapid cooling and expansion, it might have frozen in certain imperfections, cosmic scars from a time before time as we know it. These remnants would have been entities of staggering density and energy. Among the most discussed are cosmic textures, domain walls, and magnetic monopoles, each a testament to a broken symmetry in the laws of physics. A domain wall, for instance, would be a two-dimensional sheet of concentrated energy, a membrane separating regions of space with different vacuum properties. To encounter one would be to face a boundary of such immense density that its gravitational pull would be unlike anything else in the universe. These defects would have been the ultimate primordial anomalies, surviving through inflation like boulders in a rushing river, and then persisting inert and unchanging throughout the long dark ages that followed. In a universe that was otherwise almost perfectly smooth and homogeneous, these pre-inflationary relics would have stood out as singular, catastrophic gravitational landmarks. Their sheer mass and density would have created titanic wells in the fabric of spacetime from the very start, acting as ultra-early seeds for cosmic structure that predated even the quantum fluctuations from inflation itself. During the Dark Ages, while other processes were slowly trying to amplify tiny ripples into galaxies, these relics would have already been massive gravitational anchors. The primordial hydrogen and dark matter drifting through the expanding darkness would have felt an irresistible pull toward these ancient defects. Matter would have begun pooling around them with incredible efficiency, jump-starting the formation of the very first large-scale structures in the cosmos. A single surviving domain wall could have acted as a vast sheet of gravitational attraction, eventually evolving into one of the great filamentary walls of galaxies we see in the universe today. A cosmic texture could have collapsed under its own gravity, creating a foundational node for a future supercluster. The distribution of galaxies and voids we observe on the largest scales might not just be the result of random quantum noise, but could instead be a direct map of where these pre-inflationary defects were frozen into the cosmos, a ghostly imprint of an era that supposedly erased all traces of itself. The hunt for evidence of this radical idea focuses on the cosmic microwave background, the oldest light in the universe. The pattern of hot and cold spots in this afterglow is a baby picture of cosmic structure. While the standard inflationary model predicts a very specific, statistically random pattern, the gravitational influence of a massive pre-inflationary defect would leave a very different signature. It could create a unique, non-Gaussian feature, an anomalously large cold spot, or a strange, circular pattern that stands out from the background noise like a thumbprint on a smooth surface. Astronomers have, in fact, identified a few such anomalies in the Planck satellite data, including a large, unexplained cold spot that has resisted all conventional explanations. While not yet confirmed as evidence of a pre-inflationary remnant, these peculiar features are exactly the kind of clue that drives this theory forward, suggesting that our universe's deepest past might not be completely lost, but merely hidden in plain sight, waiting for us to decipher its ancient encoded message. Just as we considered the decay of sterile neutrinos and supersymmetric particles, another candidate from that same elegant theoretical framework could have painted the Dark Ages with its own fading light. This is the gravitino dark matter decay theory, and to understand it, we need to meet a truly fundamental character, the graviton. In our current understanding, the graviton is the hypothetical particle that mediates the force of gravity, the messenger of spacetime curvature itself. Supersymmetry, the grand theory linking matter and force particles, gives this graviton a superpartner, the gravitino. This particle is fascinating because it's a unique hybrid. It's a fermion, a matter particle, but it also possesses the spin properties of a gravitational force carrier. If gravitinos exist and were produced in the hot, dense early universe, they are a prime candidate for what dark matter could be. But there's a catch that makes them incredibly consequential for the Dark Ages. Depending on the specific version of supersymmetry, gravitinos might not be perfectly stable. The instability of gravitino dark matter is the key to this entire concept. These particles, if they constitute the invisible bulk of the cosmos, would not last forever. Each gravitino would eventually undergo a spontaneous decay, transforming its mass into a cascade of lighter, more familiar particles. The specific decay products depend on the model, but a very common and impactful pathway is the decay into a photon and a neutrino, or into other pairs of standard model particles. Now imagine this process unfolding across the vast, dark universe. Trillions upon trillions of these invisible gravitinos, permeating every cubic light-year of space, are all ticking clocks. One by one, over millions of years, they blink out of existence, and in that final moment, each one releases a burst of high-energy radiation. This wouldn't be a dramatic, simultaneous flash. It would be a continuous, universal drizzle of energetic particles, a slow and steady rain of energy falling into the darkness. The most significant of these decay products for the story of the Dark Ages is the high-energy photon, particularly in the X-ray and gamma-ray part of the spectrum. This creates a pervasive and universal background of X-ray radiation, a faint glow that emanates from the dark matter itself, bathing the entire cosmos in a deep, penetrating light. This is not the brilliant, focused light of a star, but something far more subtle and uniform, a soft X-ray haze that fills the void. This background radiation has two profound and direct effects on the primordial hydrogen gas that was the only other ingredient in the universe at that time. First, it contributes to the process of cosmic reionization. The neutral hydrogen atoms, which had been peacefully holding onto their electrons since the universe cooled down after the Big Bang, were now being constantly bombarded by these high-energy X-ray photons. Each photon carried enough energy to knock an electron loose from a hydrogen atom, effectively ionizing it and creating a free electron and a proton. This process would have been happening everywhere all the time, slowly but surely converting the neutral intergalactic medium into a slightly ionized plasma, long before the first stars ever switched on to do the job more violently. Second, this pervasive X-ray background acts as a universal space heater. When an X-ray photon ionizes a hydrogen atom, it doesn't just free the electron, it also gives that electron a significant kick of kinetic energy. These energized electrons then collide with other atoms and with the cosmic microwave background photons, distributing their energy as heat throughout the gas. This gentle, persistent heating from gravitino decay would have kept the primordial gas warmer than it would otherwise have been. This has a critical impact on star formation, especially for the smallest structures. For a small cloud of gas to collapse under its own gravity and form a low-mass dwarf galaxy, the gas needs to be cold. Cold gas is sluggish and can radiate away its energy, allowing it to condense. Warm gas, however, has higher internal pressure and vigorously resists gravitational collapse. The heating from the gravitino X-ray background would have made it exceptionally difficult for these smallest galactic building blocks to form, effectively suppressing the birth of the faintest, earliest dwarf galaxies. This provides another potential solution to the missing satellites problem, where our simulations predict many more small galaxies around the Milky Way than we actually observe. The timeline of this decay process is everything. If gravitinos decayed too quickly, their energy would have been injected into the universe when it was still very hot and dense, and the effect would have been washed away, leaving no distinct signature on the Dark Ages. If they are too stable, they would still be decaying today, and we might detect their signal in the modern X-ray background. The sweet spot for this theory is a gravitino lifetime that places the bulk of their decays squarely within the hundreds of millions of years of the Dark Ages. This would mean that the universe was being partially reionized and gently heated by dark matter for a significant portion of its early history, a process that would have subtly but permanently altered the schedule and character of the cosmic dawn that followed. The hunt for evidence of this is focused on two fronts. Astrophysicists use X-ray space telescopes to scan the diffuse cosmic X-ray background, searching for an unexplained isotropic component that cannot be attributed to known sources like distant quasars or hot gas in galaxy clusters. Any leftover, unexplained glow could be the fossil imprint of decaying gravitinos. Simultaneously, cosmologists use precise measurements of the large-scale structure of the universe and the timeline of reionization from the cosmic microwave background to look for signs that the universe was partially ionized earlier than stellar sources alone can explain. Finding such evidence would not only illuminate a hidden chapter of cosmic history, but would also provide a direct window into the world of supersymmetry, revealing the final, fading moments of gravity's hypothetical shadow particle. Our exploration of the Dark Ages now leads us to a frontier where the very stage of reality becomes uncertain, a concept that challenges our understanding of space and time at the most fundamental level. This is the quantum gravity foam fluctuation theory. To grasp its radical premise, we need to venture down to scales 1 billion trillion times smaller than an atomic nucleus, into the realm where the smooth, continuous spacetime described by Einstein's general relativity is believed to break down. Here, according to the principles of quantum mechanics, the fabric of the cosmos is no longer a static backdrop. Instead, it is theorized to be a seething, turbulent froth, a chaotic sea of virtual particles popping in and out of existence and microscopic wrinkles in spacetime itself. This is the quantum foam, a dizzying concept where the concepts of here and now lose their definite meaning, and the geometry of the universe is in a constant state of violent, unpredictable fluctuation. Throughout most of cosmic history, these fantastically small fluctuations are just background noise, far too tiny to have any noticeable effect on the large-scale universe. But the theory proposes that during the unique conditions of the Dark Ages, this microscopic chaos might have been granted a cosmic megaphone. In the standard inflationary model, the seeds for all structure are the quantum fluctuations from the inflationary epoch, stretched to macroscopic size and then slowly amplified by gravity over billions of years. The quantum foam theory offers an alternative or perhaps a supplement to this story. It suggests that the universe, as it expanded and cooled during the Dark Ages, was not a perfectly smooth, passive entity. Instead, the inherent frothiness of spacetime at the quantum level could have been spontaneously generated and then frozen into the fabric of the cosmos as it cooled, much like the complex, fractal patterns that form when a liquid suddenly freezes. These frozen quantum jitters would have created their own set of random, minuscule density variations, superimposed on top of the fluctuations from inflation. This dual origin for cosmic seeds would have profound consequences for the distribution of matter we see today. The pattern of galaxies and voids predicted by pure inflationary models has a specific statistical fingerprint, a predictable level of clustering and smoothness on different scales. If the quantum foam contributed a significant number of these initial wrinkles, it would have imprinted a different statistical signature onto the universe. The frothy, random nature of these spacetime fluctuations could have produced a distribution of structures that is subtly, but detectably, more clumpy or grainy on certain scales than the standard model allows. It's the difference between a surface smoothed by a master plasterer and one that has a fine, inherent texture from the material itself. the grand cosmic web might not just be the amplified echo of inflationary quantum noise, but also the fossilized imprint of spacetime's own turbulent, foamy nature writ large across the heavens. The hunt for evidence of this quantum signature is one of the most challenging endeavors in modern cosmology. Astronomers are using the most detailed three-dimensional maps of the universe ever created, charting the positions of millions of galaxies to look for statistical anomalies in their clustering. They are searching for a specific kind of deviation from Gaussian randomness, a telltale sign that the initial conditions were not solely set by simple inflation, but were also influenced by the chaotic, granular fluctuations of a foamy spacetime. Furthermore, the very act of light traveling across billions of light-years from distant quasars could be affected by this foam. If spacetime has a fundamental graininess, it could subtly scatter or delay the highest energy photons over their immense journeys, an effect that ultra-sensitive gamma-ray telescopes are now attempting to detect. Finding such evidence would be a monumental leap, bridging the greatest unsolved problem in physics, the unification of gravity and quantum mechanics with the practical history of our cosmos, revealing that the silent dark ages were actually alive with the faint, residual churn of spacetime itself. Where do the magnetic fields that thread through every galaxy and permeate the vast spaces between them actually come from? It's a question that leads us to a theory where the silent dark ages were not so silent after all, but were instead a cosmic forge, a place of immense, unseen turbulence that took the faintest whispers of magnetism and amplified them into a fundamental force of nature. This is the primordial magnetic field amplification theory, and it posits that incredibly weak seed fields, perhaps generated in the violent moments after the Big Bang or by the very first cosmic structures, were stretched, twisted, and supercharged during this era into the potent fields we detect today. To understand this process, we need to envision the primordial universe not as a perfectly still void, but as a dynamic and seething entity. As the first gravitational structures began to form, pulling in dark matter and gas, the ordinary matter, the hydrogen and helium plasma didn't just fall in smoothly. It cascaded and swirled, creating vast, chaotic motions and whirlpools within the collapsing gas clouds. This is the cosmic turbulence the theory relies on. Think of it like stirring a cup of coffee with a tiny, microscopic magnet at the bottom. Your spoon represents the turbulent motions of the gas, and the weak magnetic field is that tiny magnet. As you stir faster and faster, the magnetic field lines aren't just passively carried along. They get caught in the flow, stretched, folded, and woven tighter and tighter. This process, known as a dynamo, is what transforms a feeble magnetic field into a powerful one. During the Dark Ages, the entire cosmos was one giant, slow-motion whirlpool, with these turbulent motions acting as a natural dynamo on a galactic scale, amplifying those initial seed fields by a factor of billions or even trillions. But where did those initial seeds come from? There are several compelling candidates, each pointing to a different dramatic origin story for cosmic magnetism. One possibility is that they are relics from the universe's very first phase transition, a moment when the electromagnetic force separated from the weak nuclear force. Much like the cracks that form in ice as water freezes, this shift in the fundamental state of the universe could have generated defects that included feeble magnetic fields. Another, even more dramatic idea involves the period of inflation itself. The same quantum fluctuations that seeded galaxies might have also produced rippling electromagnetic waves, leaving behind a faint, primordial magnetic imprint across all of space. Or the seeds could have been sown by the first cosmic batteries, where the gentle pressure differences in spinning protogalactic clouds acted like a kind of cosmological generator, creating a small electric current that in turn produced a weak magnetic field. No matter the origin, the Dark Ages provided the perfect conditions to take these embryonic fields and give them cosmic significance. Once amplified, these magnetic fields became far more than just a curiosity. they became an active player in the drama of structure formation. Their influence was particularly crucial in the birth of the very first stars. As a massive cloud of primordial gas begins to collapse under its own weight, it naturally starts to spin, conservation of angular momentum causing it to rotate faster and faster, much like a figure skater pulling in their arms. Without any opposing force, this spin would become so rapid that it would fling the material outward, preventing the cloud from collapsing all the way into a dense star. This is where the newly strengthened magnetic field stepped in. The field lines now woven through the gas acted as a cosmic brake, a magnetic friction that connected the inner, fast-rotating parts of the cloud to the outer, slower-moving regions. This process, known as magnetic braking, efficiently transferred angular momentum away from the central core, allowing it to continue its inward collapse. Without this magnetic intervention, the first star-forming clouds might have torn themselves apart, dramatically altering the entire star formation history of the universe. Furthermore, these fields played a vital role in shaping the very architecture of star birth. They guided the flow of material, channeling gas along the field lines and helping to form the first protostellar disks, the swirling platters of gas and dust from which stars and their planetary systems coalesce. They also provided a pathway for energy to escape. As the gas collapsed, it needed to shed its thermal energy to cool down and condense further. Magnetic fields facilitated this by supporting waves and outflows that could carry away energy and momentum, preventing the central core from overheating and stalling its own growth. In this view, the magnetic fields acted as a hidden regulator, a set of cosmic rails that guided the chaotic process of gravitational collapse into the orderly formation of the first stellar nurseries. The Dark Ages, therefore, were not just a time of gravitational assembly, but also a period of intense electromagnetic organization, where the invisible scaffolding for all future star formation was being meticulously erected in the darkness. But what if the Big Bang wasn't a singular, absolute beginning, but merely the latest in an infinite series of cosmic rebirths? This is the extraordinary premise of the ekpyrotic or cyclic universe theory, a model that completely recontextualizes the Dark Ages, transforming them from a unique, one-time event into a recurring, perhaps even necessary, chapter in an endless cosmic saga. In this breathtaking vision, our entire universe is the result of a collision between two higher dimensional membranes, or branes, existing in a bulk space. This collision manifests as our Big Bang, but it wasn't the first. It was simply the most recent turning point in a cycle that has repeated countless times before. Each cycle involves the universe expanding, evolving, and eventually contracting, leading to a new collision and a new Big Bang. In this eternal rhythm, the Dark Ages are not a prelude to a single dawn, but a regular period of quiet consolidation that follows every cosmic reset. This cyclical nature offers a profound new perspective on the contents of the Dark Ages. According to this theory, our universe did not emerge from a state of pure, featureless simplicity. Instead, the Big Bang was a violent, energetic reboot that inherited some residual information from the universe that came before. The dark matter that dominates our cosmos, and perhaps even the largest gravitational wells that would become superclusters of galaxies, might not be brand new creations. They could be cosmic ghosts, the faint gravitational echoes of structures that existed in a previous cosmic cycle. Imagine the universe before ours ended in a big crunch. Its galaxies, black holes, and dark matter halos were compressed and scrambled in the collision, but their fundamental gravitational signature wasn't entirely erased. This residual memory could have been imprinted onto the new universe as a set of pre-existing gravitational irregularities, a hidden template for structure laid down before our own time even began. These inherited gravitational imprints would have had a dramatic effect on the so-called Dark Ages of our cycle. Instead of starting from a state of near-perfect smoothness defined only by quantum fluctuations, the primordial soup of our universe would have been seeded with these fossil over densities from its very first moment. This means the process of structure formation wouldn't have had to start from scratch. While the ordinary matter was a hot, ionized plasma immediately after the bang, the dark matter, potentially a relic population from the previous cycle, could have begun clustering immediately around these pre-existing gravitational seeds. The Dark Ages, then, would not have been a time of waiting for the first tiny ripples to grow. Instead, they might have been an era where matter was already flowing into an ancient, preordained cosmic architecture. The formation of the very first stars and galaxies could have been significantly accelerated, happening in preferred locations dictated by this hidden blueprint from a bygone era. The most tantalizing evidence for this radical idea could be etched into the oldest light we can see, the cosmic microwave background. This fossilized radiation is a snapshot of the universe just 400,000 years after the Big Bang, and its pattern of hot and cold spots is the ultimate record of the initial conditions. In the standard single bang model, these fluctuations are expected to be random and Gaussian. However, if our universe inherited a gravitational skeleton from a previous cycle, it might leave a distinctive, non-random signature in this background glow. Specific, large-scale anomalies in the CMB, such as unexpected alignments of hotspots or an unusual lack of correlation on the very largest scales, could be the cosmic fingerprints of this pre-bang structure. Some cosmologists point to features like the mysterious cold spot or certain statistical asymmetries in the Planck satellite data as potential, though highly debated, hints that our universe's first moments were not a clean slate, but were instead influenced by the ghostly remains of a cosmos that lived and died before our own. Finding definitive proof would mean that the long, dark silence was not an absolute beginning, but a transitional phase in an infinite cosmic story, a recurring night that falls after every celestial day. Now, let's shift our focus from the grand, sweeping forces of the cosmos to the specific, dynamic players that began to emerge within it. We've talked about how the first stars, especially the massive ones, lived fast and died young, often collapsing into stellar mass black holes. But what if these newly formed black holes didn't just sit quietly in the darkness? The black hole accretion feedback theory proposes that these gravitational pits became active, powerful agents of change, their influence rippling outward to shape the very environment around them, effectively dictating where and when new stars could be born. The engine for this transformative process is a phenomenon known as accretion. Imagine a newborn stellar mass black hole, the remnant of a colossal star's death, sitting at the heart of a vast cloud of pristine hydrogen gas. This gas hasn't yet collapsed to form new stars. The black hole's immense gravity acts like a cosmic vacuum, relentlessly pulling this gas inward. But the gas doesn't fall straight in. It has some angular momentum, causing it to spiral around the black hole, flattening into a superheated, whirling disk, an accretion disk. As the gas particles in this disk rub against each other under fantastic pressures and speeds, they heat up to temperatures of millions of degrees, causing the disk to glow with an intense, piercing light across the electromagnetic spectrum, from X-rays to ultraviolet radiation. In some cases, the black hole's powerful magnetic fields and rapid rotation can also funnel some of this infalling material into focused, narrow beams that are shot outward at nearly the speed of light. These are relativistic jets, cosmic blowtorches that can carve their way through the interstellar medium for thousands of light years. It's this powerful output of energy, the intense radiation and the high-speed jets, that constitutes the feedback. And for the nascent structures of the Dark Ages, this feedback was a profoundly disruptive force. The primary requirement for a cloud of gas to collapse and form a star is that it must be cold. Cold atoms move slowly and can clump together easily. The fierce radiation from an accreting black hole works directly against this. The high-energy photons, particularly X-rays and ultraviolet light, slam into the surrounding neutral hydrogen gas. They do two critical things. First, they ionize the gas, stripping electrons away from their atoms. Ionized gas or plasma is much hotter and has higher internal pressure, making it fiercely resistant to gravitational collapse. Second, this radiation directly heats the gas, giving its atoms more kinetic energy, causing them to bounce off each other more vigorously, further preventing the quiet, slow condensation needed for star formation. The result is that in the immediate vicinity of an active black hole, the gas becomes too hot and too agitated to form new stars. The black hole effectively sterilizes its own neighborhood, creating a localized bubble of suppressed star formation within the larger dark cloud. This process would have created a fascinating and uneven patchwork across the early cosmos. Picture a vast, dark nebula, pregnant with the potential to birth thousands of new stars. In one region, a black hole switches on, its accretion disk flaring into brilliance. A wave of intense radiation expands outward from this point, heating and ionizing a large volume of space around it. Within this bubble, star formation is put on hold, the stellar birth rate plummeting to near zero. Meanwhile, in another part of the same cloud, far enough away to be shielded from this energetic onslaught, the gas remains cold, dark, and quiet. Here, gravity can work unimpeded, and the first protostars continue to condense and ignite. The universe wouldn't have lit up in a uniform, simultaneous dawn. Instead, the end of the Dark Ages would have been a staggered, mosaic-like transition, with brilliant islands of activity and light separated by vast, silent voids that were being actively kept dark by the very black holes that the first stars had left behind. This feedback mechanism provides a natural explanation for why star formation is so inefficient. It suggests that from the very beginning, the universe had built-in regulators, cosmic cycles of creation and suppression that prevented all the available gas from being used up in one frantic burst of stellar birth. The darkness wasn't just passively receding, it was being actively managed. To truly grasp the origins of cosmic structure, we need to journey back to a time before even the first atomic nuclei had formed, to an era of unimaginable heat and density that makes the Dark Ages seem tranquil by comparison. This brings us to a fascinating proposition known as the lepton-photon universe phase theory, which suggests the blueprint for everything was cast not during the darkness, but in the universe's first brilliant flash of light. In the earliest microseconds after the Big Bang, the cosmos was not filled with hydrogen and helium, but was instead a seething, opaque ocean of energy. This primordial soup was dominated by two key ingredients: photons, the particles of light, and leptons, a family of elementary particles that includes the familiar electron and its more exotic cousins, neutrinos. For a fleeting but critical moment, this lepton-photon plasma was the universe. Within this incredibly dense and hot medium, theorists propose that profound phase transitions occurred. Think of a phase transition like water freezing into ice. It's a sudden, dramatic shift in the state and properties of a substance as it cools. In the lepton-photon universe, as the expansion caused temperatures to plummet, the fundamental fields and particles underwent their own kind of cosmic freezing. These transitions wouldn't have been perfectly smooth and uniform across the entire cosmos. Tiny quantum fluctuations, the same kind that inflation amplified, could have caused the transition to happen at slightly different rates or in slightly different ways in different regions. This would have created a patchwork of varying densities and pressures within the plasma, subtle ripples in a sea of pure energy. These were not the density variations of matter as we know it, but rather fossilized imprints in the very fabric of the energetic universe, imperfections frozen in time as the cosmos cooled and evolved. The profound implication is that these fossil imbalances from the lepton-photon era did not simply vanish when the universe moved on to its next chapter. Instead, they were locked into the cosmic record, serving as the ultimate gravitational template for all that followed. When the universe cooled enough for protons and neutrons to form, and then later, during Big Bang nucleosynthesis, for those nuclei to capture electrons and create neutral atoms, the process didn't happen on a perfectly blank slate. The slight overdensities left over from the lepton-photon phase transition acted as preferred locations. Gravity, ever so slight at first, would have found these regions ever so slightly more attractive. The primordial hydrogen and helium, once they formed, would have felt a gentle but persistent pull toward these ancient wrinkles. The vast, dark clouds of gas that would one day collapse into the first stars didn't simply congeal at random. They were guided into existence by a pattern set in motion when the universe was just a fleeting, brilliant fireball of light and leptons. The great cosmic web of galaxies and voids we see today may in fact be a ghostly, amplified echo of a pattern woven into reality in its very first moments. This theory offers a powerful and elegant link between the quantum world and the grand scale of the cosmos, suggesting that the largest structures have their roots in the smallest of phenomena. It provides a potential explanation for why we see certain preferred scales in the distribution of galaxies, patterns that might be difficult to explain if the initial seeds came solely from a later epoch. The hunt for evidence of this is intertwined with our most precise observations of the cosmic microwave background and the large-scale structure of the universe. The specific statistical signature of these lepton-photon era fossils would be subtly different from other proposed initial conditions, a unique fingerprint waiting to be decoded in the map of the heavens. It's a compelling reminder that the universe's history is a continuous chain of cause and effect, where the events of the first fleeting seconds irrevocably shaped the long, dark night that followed, and ultimately the star-filled cosmos we call home. Now we venture into one of the most profoundly counterintuitive concepts in all of physics, a theory that suggests the vast, three-dimensional reality we experience might be nothing more than an elaborate illusion, a cosmic projection. This is the holographic principle application theory. To grasp this, imagine the universe as a giant, immersive movie. We are inside the film, experiencing its depth, its textures, and its drama in full 3 dimensions. But the holographic principle proposes that all the information needed to create this entire rich, 3-dimensional experience, every galaxy, every star, every person, is actually encoded on a distant, 2-dimensional surface that surrounds us, much like the data on a Blu-ray disc contains the entire movie. Our reality, in this view, is a holographic projection, and the Dark Ages become the era when this cosmic projector was first booting up, its foundational code being written onto the edge of the observable universe. This principle finds its roots in the study of black holes, where physicists like Jacob Bekenstein and Stephen Hawking discovered a startling fact. The maximum amount of information or entropy a black hole can contain is not proportional to its volume, as you might expect, but to the surface area of its event horizon. This was the first hint that perhaps the physics of a volume of space could be entirely described by information residing on its boundary. Extending this mind-bending logic to the entire cosmos, the holographic principle suggests that the information defining everything within our observable universe is stored on a spherical shell at its farthest edge, the cosmic horizon. Every event, every particle, every force we experience is a translation of data encoded on this ultimate celestial hard drive. Applying this to the Dark Ages transforms our understanding completely. Instead of structure forming from random quantum fluctuations within the 3-dimensional space, the initial conditions for all cosmic structure, the locations of the first overdensities that would become galaxies, might have been predetermined by the specific pattern of information written on this primordial horizon. The large-scale architecture of the universe wasn't emerging from chaos, it was being decoded from a cosmic blueprint. During the long, dark silence, while the universe was a simple, expanding soup of hydrogen and dark matter, this holographic data was actively shaping the void. The microscopic quantum ripples on the 2-dimensional boundary were being translated, through the complex laws of quantum gravity, into the gravitational potentials that would guide the flow of matter in the three-dimensional interior. Think of it like the surface of a soap bubble. Tiny, intricate vibrations and patterns on the surface of the bubble dictate the complex, shimmering play of light and color within the bubble's entire volume. Similarly, the specific arrangement of quantum bits or qubits on the cosmic horizon during the Dark Ages directly mapped out where gravity would be slightly stronger or weaker, creating the gravitational wells that would eventually pull in matter to form the first stars and galaxies. The distribution of galaxies we see today, the great walls and vast voids, may not be a random statistical outcome, but a direct three-dimensional readout of a two-dimensional data structure that was fixed in the universe's youth. The implications of this for the nature of the Dark Ages are staggering. It suggests that the fate of the cosmos was, in a sense, predetermined from its very first moments, not by destiny but by information theory. The potential for every galaxy, every planetary system, and every conscious being was already implicit in the data encoded on the boundary. This could provide a natural explanation for why the universe appears so finely tuned on large scales, with a uniformity and statistical pattern that seems almost too perfect. It's because the underlying code that generated it has a specific, coherent structure. The long wait of the Dark Ages, in this view, was not a period of passive cooling, but an active processing phase where the universe was translating its foundational, two-dimensional instructions into the rich, three-dimensional reality that was about to dawn with the first starlight. The darkness was not empty, it was saturated with information waiting to be rendered. But what if we've been looking at the cosmic blueprint all wrong? What if the mysterious dark matter that we've invoked to explain the gravitational glue of the cosmos is not a substance at all, but a sign that our understanding of gravity itself is incomplete? This is the radical proposition of Theory 22, the modified Newtonian dynamics, or MUND, in the early universe. Imagine a universe where Isaac Newton's famous law of universal gravitation and even Einstein's majestic theory of general relativity don't tell the whole story. MUND proposes that on the very largest scales and in environments of extremely weak acceleration, like the outer rims of galaxies or the vast, diffuse depths of the early cosmos, gravity behaves differently. Instead of the force of attraction falling off with the square of the distance as we've always known, it transitions to a new regime, creating a stronger gravitational pull than standard physics would predict. In this view, the extra gravity we attribute to the unseen hand of dark matter is actually just gravity itself wearing a different face when the cosmic lights are dim. Applying this revolutionary idea to the Dark Ages completely reframes the narrative of cosmic structure. In a MUND-governed early universe, the process of building galaxies wouldn't have relied on the slow, patient accumulation of dark matter halos. Without the need for dark matter to provide the initial gravitational wells, the ordinary baryonic matter, the hydrogen and helium gas would have been the sole actor on the stage. And under MUND-altered rules of gravity, this gas could have clumped together and collapsed into structures with startling speed. The faint ripples in the density of the primordial plasma would have felt a significantly stronger gravitational tug from one another. This enhanced gravity would have acted like a cosmic catalyst, dramatically accelerating the growth of those first overdensities. Where the standard model requires hundreds of millions of years of slow gravitational aggregation, a MUND-like gravity could have forged the first protogalactic clouds in a much shorter time, potentially leading to an earlier and more vigorous dawn of the first stars. The long, dark silence might have been cut short by a gravity that was simply more effective at its job of building things in a young, low-density cosmos. The implications of this for the universe we observe today are profound. MUND offers a potential solution to several persistent puzzles that challenge the dark matter paradigm. For instance, the observed rotation curves of galaxies, how fast stars and gas orbit the galactic center, are perfectly explained by Mund's prescription for stronger gravity in low acceleration regimes without needing to invoke any invisible matter. When we look back at the properties of the very first, most pristine galaxies starting to form at the end of the Dark Ages, their masses, sizes, and rotation speeds could carry a unique signature of this alternative gravitational history. If the first structures appeared surprisingly mature and organized for their cosmic age, it could be a clue that Mund rules were in play, enabling a more direct and efficient path from smooth gas to structured galaxy. This theory fundamentally challenges a cornerstone of modern cosmology, suggesting that we may be on a wild goose chase for a particle that doesn't exist, while the true answer lies in a deeper, more nuanced law of nature that reveals itself only in the most extreme and subtle environments, like the profound quiet of the universe's formative years. Now, let's listen for the faintest possible echo of creation itself, a vibration so subtle it has been humming through the cosmos since the very first instant. This is the primordial gravitational wave background theory, and it asks us to imagine that the silent Dark Ages were not truly silent, but were instead filled with a fundamental, universe-wide hum, a background of ripples in the very fabric of spacetime. These aren't waves of light or sound, they are literal stretches and squeezes of spacetime itself, generated by the most violent events imaginable: the explosive birth of the universe and the hyper-accelerated expansion of inflation. Just as the Big Bang left behind a fossil glow of light, the cosmic microwave background, theorists believe it must have also produced a background of gravitational waves, a permanent, ringing vibration etched into the geometry of everything. During the long Dark Ages, while the universe was a cold, dark, and neutral sea of hydrogen, this gravitational wave background would have been a pervasive, if imperceptible, presence. Picture the cosmos as a vast, still pond. The gravitational waves are like incredibly gentle, continuous ripples moving across the surface of this pond. They don't carry water with them. Instead, they momentarily distort the surface itself, causing a slight, rhythmic stretching and compressing of distances. In our cosmic pond, these spacetime oscillations would have been gently and constantly perturbing the distribution of matter. A cloud of primordial hydrogen gas drifting in the void would have been subtly and rhythmically squeezed and stretched by these passing waves. The effect would have been minuscule, far too small to directly tear a cloud apart, but over millions of years, this persistent, oscillating gravitational tug could have acted as a catalyst, providing the tiniest extra nudge to regions of gas that were already on the very brink of gravitational collapse. The true power of these waves lies in their ability to impart a specific, coherent motion to the primordial gas. Imagine two particles of hydrogen floating near each other in a vast, dark cloud. As a gravitational wave passes through, it momentarily changes the distance between them, first pulling them slightly closer together, then pushing them slightly further apart. This rhythmic motion, when multiplied across the sextillions of particles in a giant gas cloud, could have helped transfer energy and angular momentum, potentially influencing how the cloud fragmented as it collapsed. The gravitational wave background would have been a universal metronome, setting a faint, rhythmic beat against which the first slow dance of structure formation unfolded. It provided a universal source of perturbation, a background stir that ensured the collapse of the first gas clouds wasn't a completely isolated event, but one that was subtly coordinated by the deepest vibrations of spacetime. The hunt for this primordial hum is one of the most challenging and exciting frontiers in modern cosmology. Our current gravitational wave detectors, like LIGO and Virgo, are marvels of engineering, but they are tuned to listen for the catastrophic crashes of black holes and neutron stars in the relatively recent universe. The primordial background is far older and fainter, a murmur compared to these modern-day shouts. To detect it, scientists are turning to the universe's most natural and precise detectors, pulsars. These are rapidly spinning neutron stars that emit beams of radio waves with the regularity of atomic clocks. By monitoring networks of these cosmic lighthouses across our galaxy with projects like the North American Nanohertz Observatory for Gravitational Waves, astronomers are looking for correlated, rhythmic timing glitches. A passing gravitational wave from the background would minutely alter the spacetime between us and a pulsar, causing its pulses to arrive a few billionths of a second early or late. By carefully analyzing the pattern of these timing shifts across dozens of pulsars over many years, we can effectively use the entire galaxy as a giant gravitational wave antenna. Finding this signal would be a direct window into the universe's first moments, probing energies and conditions that are forever inaccessible to particle colliders. The specific properties of this background, its strength and its spectrum of frequencies would tell us unequivocally about the physics of inflation and the nature of the Big Bang itself. It would confirm that the Dark Ages, a period we perceive as one of profound quiet, was actually thrumming with the energetic aftermath of creation, a vibrational memory of the universe's violent birth that gently guided the gas of the Dark Ages into the first brilliant structures of light. So far, we've explored dark matter as a collection of aloof particles and as a cosmic superfluid, but what if its true nature was more social? This brings us to a compelling variation on the dark matter theme, the self-interacting dark matter halo core theory. In our standard model, dark matter is collisionless. The particles pass right through each other as if they were ghosts in a crowded room, completely unaware of one another's presence. Their only interaction is through gravity. This theory radically departs from that assumption, proposing that dark matter particles can, in fact, feel a force other than gravity. Imagine if they had their own version of a weak nuclear force, allowing them to bump into and scatter off one another. This single added property of self-interaction transforms dark matter from a passive substance into a dynamic fluid with profound consequences for the architecture of the cosmos. When dark matter particles can collide and exchange energy, they begin to behave less like a swarm of independent entities and more like a collective. Picture a vast cloud of these particles collapsing under their own gravity to form one of the first dark matter halos. In the standard model, without any way to dissipate energy, the particles would simply oscillate back and forth in the gravitational well, piling up in a very dense, sharp peak at the very center, what cosmologists call a cusp. But if the particles can interact, something remarkable happens. As they fall inward, they collide and scatter, effectively creating a form of friction. This friction allows them to transfer energy and angular momentum from the inner, faster-moving regions to the outer parts of the halo. It's a self-regulating process, much like stirring a cup of hot coffee. The liquid in the center swirls vigorously, but through friction with the rest of the cup, it eventually settles into a more uniform, smoothed-out state. The result is that the extreme central density is erased, replaced by a large, constant density core at the halo's heart. Instead of a sharp, steep peak, you get a soft, rounded hill. This transformation from a cuspy profile to a chord one has a direct and dramatic impact on the process of star formation during the Dark Ages. The gravitational potential, the depth and shape of the gravitational well that the dark matter halo creates is fundamentally altered. A cuspy halo has an intensely steep gravitational slope, a deep, narrow pit that pulls matter inward with ferocious strength. A chord halo, by contrast, creates a much shallower, more gradual gravitational basin. It's the difference between diving into a deep, narrow well and wading into a wide, shallow pond. For the primordial hydrogen gas, this distinction is everything. To collapse and fragment into stars, the gas must fall deep into the gravitational well, cool down, and condense to extremely high densities. A steep, cuspy potential makes this easy. Gravity does most of the work, forcefully compressing the gas. But in the shallow potential of a core dark matter halo, the pull of gravity is significantly weaker at the most critical point, the center. The gas feels a much more gentle attraction, making it far more difficult to achieve the densities required to trigger runaway collapse and ignite the nuclear fires of the first stars. This provides an elegant and compelling explanation for one of the key observational puzzles in early universe astronomy: the surprising faintness of the earliest galaxies we are now discovering with telescopes like James Webb. Our standard collisionless dark matter simulations often predict that the first small galaxies should have been brighter and more actively forming stars than what we actually see. If the first dark matter halos had soft cores instead of sharp cusps, it would naturally put the brakes on star formation. The gas would still be drawn into the halo, but it would linger in a more diffuse state, unable to condense efficiently. Star formation would be a slow, stuttering process rather than a dramatic burst, resulting in galaxies that are inherently dimmer and more anemic in their youth. The self-interacting nature of dark matter could have acted as a cosmic regulator, a built-in governor that prevented the universe from using up its star-forming fuel too quickly, ensuring that the cosmic dawn was a gradual sunrise rather than a sudden, brilliant flash that burned out too soon. Now we arrive at a theory that ventures into truly speculative territory, a concept where the bedrock of physics itself is challenged to explain the darkness. This is the tachyonic dark matter instability theory. To understand its premise, we must first confront the tachyon, one of the most controversial ideas in theoretical physics. A tachyon is a hypothetical particle that, by its very definition, always travels faster than the speed of light. In our familiar reality, Einstein's theory of relativity establishes light speed as the ultimate cosmic speed limit, a barrier that cannot be crossed by any object with mass. Tachyons turn this principle on its head. They are conceived as particles that can only exist beyond this limit, forever condemned to move at superluminal velocities. They are not something that can be accelerated to light speed. They are born into a state of existence where the normal rules of causality and time ordering might not apply in any way we recognize. While no experimental evidence for them exists, they remain a fascinating mathematical possibility in certain extensions of quantum field theory. This theory proposes that the mysterious substance we call dark matter was not made of WIMP or Axions, but was instead composed of a sea of these superluminal tachyons in the universe's infancy. In this model, the Dark Ages were not a period of stable, cold matter waiting to collapse, but rather an era of precarious cosmic equilibrium. The tachyonic dark matter existed in what physicists call a false vacuum state, a seemingly stable configuration that is not, in fact, the lowest possible energy state for the universe. It was a cosmic house of cards, looking solid and permanent, but secretly poised for a catastrophic collapse. Then, as the universe expanded and cooled during the Dark Ages, it crossed a critical threshold. This triggered a profound phase transition, a sudden and universal shift in the state of the dark matter field, much like supercooled water instantly flash freezing. The once stable tachyonic field became unstable, causing the tachyon particles to rapidly decay out of existence. The consequence of this universal decay would have been a release of energy of almost unimaginable scale. When the tachyonic dark matter decayed, its immense mass energy, which had previously been tied up in this exotic form, was suddenly converted. It transformed into a torrent of standard model particles, a flood of high-energy photons, electrons, positrons, and quarks that erupted across the entire cosmos simultaneously. This wouldn't be a localized event like a supernova. It would be a universe-wide flash, a sudden, brilliant burst of energy igniting in the heart of the darkness. The entire cosmos, for a fleeting moment, would have been filled with an intense, penetrating radiation field, a firestorm of particles born from the death of the faster-than-light dark matter. This colossal, instantaneous energy injection would have had one primary and transformative effect: It would have ripped the universe apart. The primordial hydrogen gas, which had been a cold, neutral fog for millions of years, was suddenly and violently assaulted by this radiation blast. The high-energy photons, particularly in the ultraviolet and X-ray range, carried more than enough power to knock electrons clean off their hydrogen atoms. In a process that was both swift and universal, the neutral intergalactic medium was blasted into a fully ionized plasma. Electrons and protons were torn asunder, and the universe was transformed from an opaque, neutral state to a transparent, ionized one in what would have been, on a cosmic timescale, the blink of an eye. This event would constitute an episode of widespread, incredibly early reionization, fundamentally altering the timeline of cosmic history. This tachyonic decay offers a radical solution to a key puzzle in modern cosmology. Observations from the Planck satellite and the James Webb Space Telescope are beginning to paint a detailed picture of the epoch of reionization, and there are hints that the process may have started earlier and unfolded more quickly than some standard models predict. A sudden, global event like a tachyonic phase transition could perfectly account for such rapid, early reionization. Instead of the slow, patchy process driven by the first isolated stars and galaxies, reionization would have been a single, dramatic cataclysm, a cosmic lightning strike that lit up the entire universe at once. The legacy of this event would be permanently imprinted on the cosmic microwave background. The specific pattern of polarization in this ancient light and the precise timeline of when the universe became transparent are sensitive probes of how reionization occurred. A very sudden, early reionization driven by a tachyonic instability would leave a unique statistical signature in this polarization data, a fingerprint that cosmologists are actively searching for. While highly speculative, this theory demonstrates the lengths to which physicists will go to explain the cosmos, daring to invoke particles that break our most fundamental rules of motion to illuminate the secrets of the long, dark night. Forget the simple three-dimensional universe of our everyday experience for a moment and journey into a realm of far greater complexity. This is the extra dimensions compactification theory, a concept that pulls its inspiration from the most ambitious framework in all of physics, string theory. To make its mathematical equations work, string theory requires that our universe isn't just made of the three spatial dimensions we know, length, width, and height, but actually has several more, perhaps 6 or 7 additional spatial dimensions that are curled up and hidden from our view on an inconceivably tiny scale. Think of a garden hose. From a distance, it looks like a simple one-dimensional line. But if you could shrink down to the size of an ant and crawl on its surface, you'd discover it has a second dimension, a circular one that wraps around. The extra dimensions of string theory are thought to be like that, fantastically small and curled in upon themselves or compactified. This theory dares to suggest that during the Dark Ages, the size and shape of these hidden dimensions were not yet set in stone. They were dynamic, evolving entities, and their final configuration had a direct and dramatic impact on the visible universe taking shape around them. The key to this idea is how these compactified dimensions influence the fundamental forces. In string theory, the properties of every particle and every force we observe, the strength of electromagnetism, the power of the strong nuclear force, even the intensity of gravity itself, are all determined by the specific geometry of these extra dimensions. It's as if the laws of physics we measure are just the shadow cast by a more complex, higher-dimensional reality. As the universe expanded and cooled during the Dark Ages, the extra dimensions were themselves settling down, finding their stable, compactified forms. But this process of stabilization might not have been perfectly uniform across the entire cosmos. Just as a sheet of ice freezing on a pond can develop cracks and variations in thickness, the compactification of these dimensions could have happened slightly differently in one vast region of space compared to another. In one part of the universe, the extra dimensions might have compactified into a tight, complex shape, while in another they settled into a slightly looser, more open configuration. This variation in the hidden geometry of space would have had a staggering consequence. The laws of physics themselves would have been different from place to place. Most critically for the story of structure formation, the strength of gravity could have varied. Gravity, in string theory, is particularly sensitive to the size of the extra dimensions. In a region where the dimensions were compactified more tightly, gravity might have been weaker, its force diluted as it spread through the additional curled-up spaces. In a neighboring region where the dimensions were a bit larger, gravity could have been significantly stronger, more potent and focused. Suddenly, the smooth, uniform cosmos of the Dark Ages is revealed to be a patchwork quilt of differing physical constants. You have zones of normal gravity right next to zones of supergravity and others of subgravity, all depending on the local, hidden architecture of reality. This cosmic unevenness would have directly and powerfully seeded the formation of the very first structures. In those regions where gravity was artificially boosted by the local compactification geometry, the process of gravitational collapse would have received a colossal head start. The primordial hydrogen and dark matter in these supergravity zones would have felt an irresistible pull, clumping together with incredible efficiency and speed. While other parts of the universe were still a slowly stirring soup, these regions would have been frenzied hubs of activity, with matter rushing inward to form the seeds of the first protogalaxies and massive star clusters at a vastly accelerated rate. The large-scale distribution of matter we see today, the great walls of galaxies and the vast, empty voids between them, might not just be a result of random quantum fluctuations. Instead, it could be a direct map of where the extra dimensions of string theory happened to compactify in a way that made gravity temporarily stronger, creating a preordained pattern of cosmic hotspots for structure formation. The darkness was not uniform, it was textured by the silent, invisible settling of dimensions beyond our perception, a process that wrote the blueprint for the luminous cosmos in a language of higher dimensional geometry. We've already explored how WIMP dark matter could have subtly heated the early universe through its annihilations, but now let's narrow our focus to a particularly elegant and specific candidate, the neutralino. In the world of supersymmetry, the neutralino stands out as a perfect, and in many ways the most popular, candidate for dark matter. It's a hypothetical particle that emerges naturally from the theory, a stable, neutral, and massive mix of the superpartners of the Higgs boson and the force carriers. Its predicted properties check all the boxes for a WIMP. It interacts only weakly with ordinary matter and has the right relic abundance to account for the dark matter we observe. But the neutralino has a particularly clean and testable signature when it annihilates, and this signature could have painted the Dark Ages with a very specific kind of light, one that would have subtly but permanently altered the recipe for the universe's very first stars. When two neutralinos collide and annihilate, they don't just produce a random spray of particles. A significant fraction of the time, the process can result in the direct production of two high-energy gamma-ray photons. This isn't just any gamma-ray emission, it's what scientists call a monochromatic or line emission. Imagine you're listening to a symphony where all the instruments are playing different notes at once. That's the general, chaotic gamma-ray background from cosmic sources like supernova and quasars. Now, imagine a single, pure, piercing tone cutting through that cacophony, a note of one specific, unwavering pitch. That's what a gamma-ray line from neutralino annihilation would sound like in the language of physics. It would be a sharp, unmistakable spike at a very precise energy in the gamma-ray spectrum, a direct and undeniable fingerprint of the particle's mass, since the energy of each photon would be equal to the mass of the neutralino itself, courtesy of Einstein's E equals mc squared. Now, let's cast this pure, spectral tone back into the darkness of the early universe. During the long Dark Ages, long before the first stars and galaxies lit up the cosmos, this annihilation process would have been happening constantly, albeit rarely, throughout the vast expanse. Everywhere that dark matter existed, which was everywhere, there was a chance for two neutralinos to meet and vanish in a flash of gamma rays. This would have created a faint, diffuse, but incredibly uniform glow of high-energy photons, a soft whisper of gamma radiation permeating the entire cosmos. This wasn't a light you could see with human eyes, but it was a pervasive and potent energy field, a cosmic background radiation of a far more energetic and penetrating kind than the microwave afterglow of the Big Bang. The universe was no longer just dark and cold. It was filled with an invisible, energetic haze, a bath of gamma rays silently raining down on the one other thing that was there, the primordial hydrogen gas. This persistent gamma-ray bath had a surprisingly specific and devastating effect on the most crucial molecule for early star formation, molecular hydrogen. You see, the very first stars couldn't form in the same way stars do today. Modern stars often form with the help of heavier elements like carbon and oxygen, which allow the gas cloud to cool and fragment efficiently. But the first stars had to form from pure hydrogen and helium, and the most effective way for this pristine gas to cool down was through molecular hydrogen. A hydrogen molecule made of two hydrogen atoms bound together has specific rotational and vibrational states. When it collides with another atom, it can get excited and then radiate away that energy as infrared light, effectively acting as a miniature refrigerator for the gas cloud, allowing it to shed heat and contract further. The entire pathway to creating the first stars hinged on the presence of this fragile molecular hydrogen. The gamma rays from neutralino annihilation acted as a cosmic wrecking ball for these delicate molecules. A single high-energy gamma-ray photon, carrying millions of times more energy than the weak bond holding the hydrogen molecule together, would slam into one of these molecules and immediately rip it apart, a process known as photodissociation. It was like using a sledgehammer to crack a soap bubble. This wasn't a gentle heating, it was a targeted destruction of the very coolant that the primordial gas clouds desperately needed. As soon as a molecule of hydrogen formed, it stood a high chance of being blasted apart by this pervasive gamma-ray background. The consequence was that the gas struggled to cool down below a certain temperature. Without efficient cooling, the clouds couldn't compress to the incredibly high densities required to ignite nuclear fusion. The formation of the very first low-mass stars could have been significantly delayed or even completely suppressed in certain regions. The universe was caught in a catch-22. The dark matter was providing the gravitational wells for structure to form, but its own annihilations were simultaneously destroying the key ingredient needed to light up inside those wells. This leads to a fascinating alternative pathway for the dawn of the first stars. With the molecular hydrogen pathway blocked or hindered by the neutralino's gamma-ray glow, the universe would have had to find another way. The only other option was to wait. Gas had to accumulate in much larger and more massive dark matter halos, halos so deep and powerful that their stronger gravitational pull could compress the gas even if it couldn't cool efficiently through molecular hydrogen. Once a cloud reached a critical mass of around 100,000 to 1 million times the mass of our Sun, a different cooling process could take over, atomic line cooling. In these massive halos, the sheer pressure and density could cause the hydrogen atoms themselves to radiate energy, allowing the gas to finally collapse. But the stars that formed from this process would have been very different. They would have been true monsters, behemoths hundreds of times more massive than our Sun, born in isolation within these vast, massive halos. So, the neutralino's ghostly gamma-ray light may have directly orchestrated the birth of the universe's first stellar titans, ensuring that the cosmic dawn was heralded not by a crowd of small, faint suns, but by the brilliant, solitary flares of colossal, once-in-a-lifetime stars. The hunt for this gamma-ray line is a primary goal for next-generation space telescopes, and finding it would not only confirm the identity of dark matter, but also reveal its active and transformative role in crafting the first chapter of the universe's luminous history. Now, let's weave a new kind of thread into our cosmic tapestry, one that originates from the most fundamental level of reality. This is the cosmic superstring reconnection theory, and it introduces an actor even more exotic than the cosmic strings we discussed earlier. Cosmic superstrings are not mere cracks in space-time. They are hypothesized to be fundamental, vibrating loops and strands of energy, relics predicted by string theory that have been stretched to astronomical scales during the universe's expansion. Imagine them as the universe's most primordial guitar strings, each one infinitely thin yet possessing immense mass energy, vibrating and moving through the cosmos at relativistic speeds. Their existence would be a direct link to the quantum gravity era, and their behavior during the Dark Ages could have painted the darkness with fleeting, brilliant sparks. The true magic of this theory unfolds when these cosmic superstrings interact. As they whip and oscillate through the void, their paths inevitably cross. When two such strings meet, something extraordinary happens. They can reconnect. Picture two incredibly thin, impossibly strong wires slicing through space. If they cross, they don't just pass through each other, they can break and instantly re-tie themselves, swapping partners in a fundamental cosmic dance. This reconnection event isn't a gentle process. The sudden reconfiguration releases a titanic burst of energy, equivalent to a significant fraction of the string's immense mass being converted directly into radiation. This energy erupts as a powerful flash of high-energy particles and electromagnetic waves, from radio waves all the way up to gamma rays. In the profound, unbroken silence of the Dark Ages, each one of these reconnections would have been a spectacular, if fleeting, firework. These energetic outbursts would have acted as the universe's first beacons, not of steady light but of powerful, localized flashes. Each reconnection event would create a transient, intensely hot and ionized bubble within the surrounding sea of cold, neutral hydrogen gas. The burst of radiation, particularly the high-energy photons, would have slammed into the nearby hydrogen atoms, violently stripping electrons from their nuclei. For a brief period, this created a small, isolated pocket of plasma, a tiny, glowing blister of transparency within the otherwise opaque cosmic fog. These weren't the large, growing ionization bubbles driven by stars or quasars. They were short-lived, pinpoint events, flickering on and off randomly across the cosmos like a field of lightning bugs in a vast, dark meadow. They provided sporadic, temporary windows through which light could, in principle, travel, punctuating the darkness with moments of violent clarity. This process of creating small, isolated ionized pockets had a subtle but crucial impact on the overall progression of the cosmos. While a single reconnection event was transient, the collective effect of countless such events happening over millions of years would have contributed to a faint background level of ionization and heating in the intergalactic medium. It was a form of pre-ionization, a gentle simmering that kept the cosmic gas from becoming perfectly cold and neutral everywhere at once. This background of sporadic energy injection could have influenced the formation of the first molecular hydrogen, the key coolant for the first stars. In regions frequently zapped by these reconnection flashes, the delicate hydrogen molecules might have been destroyed as quickly as they formed, slightly altering the local conditions for star birth. The universe wasn't just waiting in the dark, it was being subtly stirred and energized by these random, fundamental events, a prelude to the more organized symphony of star formation that was still to come. The search for evidence of cosmic superstrings is a challenge that pushes observational astronomy to its limits. One of the most promising methods involves their gravitational footprint. These ultra-dense strings would have a profound effect on the light from distant objects. As a superstring moves between us and a distant galaxy, its immense gravity would act as a gravitational lens, but in a very unique way. Instead of creating a single magnified or distorted image, it could potentially create two identical mirror image copies of the same galaxy, a phenomenon known as the Kaiser-Stebbins effect. Astronomers are meticulously scanning deep field images from telescopes like Hubble and James Webb, looking for these telltale double images aligned in a perfectly straight line. Finding just one such pair would be monumental, providing direct evidence for these fundamental cosmic filaments and confirming that the Dark Ages were not a time of passive waiting, but were dynamically shaped by the violent reconnections of the universe's most elementary strings. Now we arrive at a concept that challenges the very independence of the cosmos's two most dominant yet mysterious components. We've explored dark energy as a constant force and as a fleeting early phenomenon. But what if its most dynamic form actively communicated with dark matter during the universe's formative years? This is the quintessence field coupling theory. Quintessence is not the static, immutable energy of a cosmological constant. Instead, it's a dynamic field, a kind of cosmic fluid that can evolve over time, its energy density and pressure changing as the universe expands. This theory takes that dynamism a step further, proposing that during the Dark Ages, this quintessence field wasn't just a passive background actor. It was actively coupled to dark matter, engaged in a continuous, invisible dialogue that exchanged energy and momentum, a conversation that fundamentally altered the rulebook for how structure formed in the cosmos. To grasp the sheer power of this idea, consider the Standard Model's portrayal of dark energy and dark matter. They are two ships passing in the night, one driving the expansion of space and the other providing the gravitational glue for structure, but with no direct interaction between them. The quintessence coupling shatters that separation. Imagine connecting those two ships with a spring. As one moves, it tugs on the other, transferring energy back and forth. In the cosmic context, as the quintessence field evolved and its energy density changed, that coupling would have allowed it to directly impart or steal energy from the dark matter particles themselves. This isn't a gravitational pull, it's a direct fifth force interaction specific to these dark sectors. The consequence is that dark matter would no longer behave as a simple, cold, and collisionless fluid. Its particles would experience an effective friction or an extra push from the evolving quintessence field, dramatically changing how they responded to the universal expansion and their own gravity. This interaction would have had two profound and distinct consequences for the architecture of the early universe. The first revolves around the clumping behavior of dark matter. In the Standard Model, dark matter is cold and sluggish, allowing it to collapse efficiently into the vast web-like halos that form the backbone of the cosmic web. But if dark matter is coupled to a dynamically evolving quintessence field, that simple picture falls apart. The energy exchange between the two could have effectively given the dark matter a form of internal pressure, making it behave more like a warm or even a hot dark matter component. This internal pressure would have worked against gravity's pull, especially within the smallest, most fragile dark matter halos. It would have smoothed out the incipient structures, erasing the tiniest density fluctuations and preventing the formation of the vast numbers of small dwarf galaxies that pure cold dark matter models predict. The cosmic web would have formed from the top down, with large-scale structures like giant galaxies and clusters emerging first, while the smallest building blocks were suppressed or erased entirely by this persistent drag from the quintessence field. The second, even more radical possibility is that this coupling could have endowed dark matter with a small but significant electric charge. In most models, dark matter is completely neutral, utterly oblivious to the electromagnetic force. But if the quintessence field acted as a mediator, it could have allowed dark matter particles to interact with photons, making them in effect minimally charged. This would have transformed the Dark Ages from a purely gravitational era into an electromagnetic one as well. Dark matter would no longer be truly dark to light. It could scatter off photons, absorb radiation, and even emit its own faint glow. A universe filled with such weakly charged dark matter would have been a much more interactive place. The primordial plasma of ordinary matter and this newly communicative dark matter would have been tightly bound together, not just by gravity, but by electromagnetic forces as well. This would have created a far more efficient transfer of heat and momentum, potentially leading to a much smoother distribution of both types of matter and preventing the violent segregation that likely occurred in the standard model. This altered dynamic would have directly impacted the very first stars and galaxies. The formation of a star requires a cloud of ordinary gas to collapse within a dark matter halo. If the dark matter itself is charged and interacting with that gas electromagnetically, the entire collapse process changes. The dark matter would exert a frictional drag on the infalling gas, potentially slowing down the collapse and altering the fragmentation of the cloud. It could have led to the formation of stars that were fundamentally different, perhaps slower to form, more massive or fewer in number. The entire timeline of the cosmic dawn would have been recalibrated by this intimate conversation between the dark sectors. Furthermore, the legacy of this charged dark matter might be written in the cosmic microwave background. The precise pattern of temperature and polarization fluctuations in this ancient light is exquisitely sensitive to any interactions between dark matter and radiation. A definitive detection of such an imprint would be revolutionary, pointing not just to the existence of dynamic dark energy, but to a deeply interconnected dark universe where its two most dominant components were once intimately linked, shaping the destiny of everything from the profound silence of the Dark Ages. Venturing into the quantum realm, we arrive at a theory that challenges the very nature of reality and our place within it. This is the application of the many worlds interpretation and quantum decoherence to the Dark Ages, a concept so profound it suggests that the universe we see around us is just one page in an infinite branching cosmic library. To understand this, we must first step back from the vast cosmos and into the bizarre world of quantum mechanics, where a single particle, like an electron, can exist in a state of superposition. It isn't definitively here or there. It occupies a blur of all possible locations simultaneously, a ghostly probability wave of existence. Only when we observe it does this wave seem to collapse into a single, definite reality. The many worlds interpretation offers a breathtakingly different explanation for this collapse. It proposes that the wave never collapses at all. Instead, at the moment of a quantum event, the entire universe splits or branches into multiple, equally real copies. In one universe, the electron is measured to be here. In another parallel universe, it is measured to be there. Every possible outcome of every quantum interaction actually occurs, spawning an ever-proliferating multiverse of alternate realities. Now, let's scale this idea up from a single electron to the entire cosmos during its formative dark ages. In the very first instance after the Big Bang, the universe was a quantum system on a cosmic scale. The tiny density fluctuations that would one day become galaxies were not yet fixed realities. They existed in a state of quantum superposition. The entire cosmic blueprint was a swirling fog of possibilities, a superposition of countless potential arrangements for the future cosmic web. There was a version of the wave function where a supercluster would form in one location, and another equally valid version where it would form in a completely different part of the sky. The universe was, in a very real sense, undecided about its own future structure. So, what forced it to make a choice? The answer lies in the process of quantum decoherence. This is the mechanism by which a quantum system loses its coherence, its ability to exhibit superposition and interference, and begins to behave classically, following the familiar, definite rules of the world we know. It happens when a quantum object becomes inextricably linked with its environment, and the information about its state is broadcast out and becomes effectively irreversible. During the Dark Ages, the environment was the universe itself. As the cosmos expanded and cooled, the primordial soup of particles and radiation constantly interacted with these superposed density fluctuations. Every time a photon scattered off a region of slightly higher density, or a neutrino passed through a potential gravitational well, it registered a tiny piece of information. This relentless, universal interaction caused the quantum superpositions of the large-scale structure to decohere. The single, shimmering wave function of possibilities effectively branched into a multitude of separate, non-communicating realities. In one branch, the subtle overdensity that would become the Virgo supercluster solidified in its specific location. In another, nearly identical branch of the multiverse, that same overdensity was slightly stronger or weaker, or was located in a different part of the void, leading to a completely different arrangement of galaxies, stars, and potentially life. Our entire cosmic history, from the patterns of the first stars to the specific placement of our own Milky Way, is therefore not a unique, preordained story. It is simply the one branch we find ourselves living in, the single cosmic timeline that decoupled from the quantum haze in a particular way, while an infinite number of other cosmic dark ages unfolded in other parallel universes, each with their own unique tapestry of light and darkness. This perspective transforms our understanding of the Dark Ages from a singular historical event into a moment of cosmic decision-making on an unimaginable scale. The profound silence was not just an absence of light, but a period where the quantum potentiality of the entire universe was solidifying into the classical reality we now observe. It forces us to ponder an even deeper question. If our cosmic structure is just one possibility among infinite others, what does that say about our own existence? In some of those branching universes, the initial conditions may have been so different that stars and galaxies never formed at all, leaving a permanent, eternal dark age. In others, the cosmic web might be far richer, with structures and phenomena we can scarcely imagine. The quiet, dark cosmos we've been exploring was the nursery not for one universe, but for all possible universes consistent with the initial laws of physics. And we are simply experiencing the one branch where the quantum dice fell in a way that allowed us to be here, looking back and wondering about the infinite shadows we left behind. From the ghostly annihilations of WIMP dark matter to the cosmic scaffolding of superstrings, and from the possibility of stars powered by dark matter itself to a universe holographically projected from its boundary, we have ventured across a breathtaking landscape of ideas, each one a testament to humanity's relentless drive to understand its origins. This journey through 30 theories has illuminated not just a hidden era of cosmic history, but the very process of scientific discovery itself, a continuous cycle of bold speculation, rigorous calculation, and the patient search for evidence in the faintest whispers of the cosmos. The Dark Ages, once considered an impenetrable void in our timeline, are now revealed as a vibrant intellectual frontier, a period that may have been shaped by everything from decaying gravitinos and interacting quintessence fields to the profound implications of a cyclic universe or the many worlds interpretation of quantum mechanics. What emerges is a powerful realization. Our universe's first chapters were likely far more complex, dynamic, and interconnected than we ever imagined. A symphony of dark and light, matter and energy, playing out on a stage whose fundamental rules might still be hiding in plain sight. The true beauty of this scientific endeavor lies not in finding a single, definitive answer, but in the rich tapestry of questions that each theory weaves. The fact that brilliant minds can propose such radically different yet equally compelling explanations for the same cosmic epoch is a feature of science, not a bug. It is the engine of progress, the tension between cold dark matter and modified gravity, the debate over the role of primordial black holes versus cosmic strings, and the search for the fingerprints of supersymmetry or extra dimensions. These are not signs of failure, but the vibrant signs of a field alive with possibility. Each new observation from telescopes like James Webb or each new data set from gravitational wave observatories has the potential to topple one theory while elevating another, guiding us closer to a more coherent story of our cosmic dawn. This is how we chip away at the unknown, not with a single hammer blow, but with the persistent collective effort of curious minds across the globe. As we bring this exploration to a close, the conversation doesn't end here. It simply expands to include you. We've navigated through concepts that challenge our perception of reality, from tachyonic instabilities that could have reionized the universe in a flash to the idea that our entire cosmos is one branch of an infinite multiverse that solidified during the Dark Ages. With so many mind-bending possibilities on the table, we have to ask, which of these 30 theories captured your imagination the most? Was it the elegant simplicity of primordial black holes acting as gravitational seeds, or the profound weirdness of a dark matter superfluid? Did the concept of dark stars, giants powered by the annihilation of the invisible, fire your curiosity, or were you drawn to the holographic principle, which suggests our three-dimensional reality is a cosmic projection? Let us know in the comments below. We are genuinely excited to hear which ideas resonated with you and sparked your own sense of wonder about the universe's deepest mysteries. If this journey into the cosmic dark ages has left you hungry for more, you're in the right place. Our channel is dedicated to peeling back the layers of the universe's greatest enigmas, from the nature of black holes and the search for alien life to the ultimate fate of everything. We regularly release deep dives just like this one, crafted to make the most complex cosmic concepts accessible and thrilling. To make sure you don't miss out on our next adventure, be sure to subscribe and hit the notification bell. It's the best way to join our community of cosmic explorers and continue unraveling the secrets of space and time together. Thank you for joining us on this incredible voyage to the edge of understanding. Keep asking big questions, stay curious about the world around you, and as always, keep looking